Welcome back. In this chapter, we'll look at creating, viewing, and modifying text files throughout the Linux operating system. By the end of this section, you should feel comfortable opening, editing, and saving the files you interact with throughout your operating system. As we begin to edit text files from the command prompt, we'll need to learn that there's a new way to edit files. Native to every Linux operating system is the editor Vim, or VI. Vim is the improved version of the original program VI and serves as a text-based file editor. As it's prevalent across all distributions, it's common to learn the skills used to wield Vim to edit your files. It's not the only option available to Linux system administrators. However, it's the most commonly deployed. And it has a bit of a learning curve. So let's take a look at how to use Vim to edit text files throughout our operating system. While I've mentioned there's alternatives, why would you choose to learn Vim? Well, I think the primary reason is that it's widely distributed across all Linux distributions. That means that when you connect to a Linux system, especially a remote system via SSH, you're likely to encounter the existence of Vim, and therefore, it would be a native toolkit across all distributions. Learning to use Vim to edit the files and settings that you need to make changes across all the systems equips a system administrator with a single text editor that they can rely on throughout all environments. Many Linux distributions only have the more simplified VI application installed. If you were to want to edit a file using VI, you would simply type the command VI followed by the file name. You can address this file name with absolute or relative pathing, as we've seen in previous sections. Once you type the command VI to launch into the editor, followed by the file name, you'll now need to start using VI-based commands in order to navigate and make the changes that you wish. Vim, VIM, is a later version of the same application, or VI improved. In more modern environments, you'll find that this is either an alternative or aliased into the command itself, meaning that when you type VI, you may even be launching VI improved. Despite which one you're using, the command will be the same. The name of the editor, followed by the file name you wish to edit. In this case, you can see an example of the command being used, vim file name. This would open the given file name in the Vim editor. Vim is known as what is called a modal editor, or that it has several different modes in which you can interact with the text you're navigating through and editing. When you first open a file name with Vim, you're simply displaying the contents of the file and can navigate throughout them using your arrow keys. There are many shortcuts throughout VI that enhance your ability to navigate or edit the various texts that you wish to interact with. However, there's quite an extensive learning curve when you wish to expand your vocabulary there. Here we'll cover the basics of being able to open, edit, and save our files. The modes within VI allow us to interact with that text in several different ways. We can use the command mode to navigate or make command-based changes to the text we see within the file. There's the extended command mode as well. The edit mode is probably the one most people require when they open a file using Vim in order to make changes to the text they're seeing. Lastly is the visual mode. The visual mode allows you to highlight blocks of text and manipulate them based on the type of interactions you'd see as a copy and paste type command. As a new Vim user, you'll need to be sure that you're always cognizant of the commands you're issuing, as you may be switching between modes or having unintended consequences as you type through the characters. Make sure that you're familiar with the different modes, how to switch between them, and then how to perform the appropriate work you see. I think one of the most important commands you should learn first is how to exit a command without saving your changes, as the various commands you'll issue may have unintended consequences. Knowing how to back out and start again can be really valuable. Here's a diagram that shows a way that we move between the modes within a Vim opened file. When we open a file, we're in command mode, and we can issue several commands in order to change or alter the behavior of the file and Vim editor. We typically enter these commands using the colon key. As I stated, one of the most important commands can be how to exit the file safely without saving any changes you may have erroneously made. If we wish to issue this command, it's initiated with the colon key followed by Q to quit. When we're ready to make changes to a file, we'll enter edit mode by hitting the I key. This will now allow us to navigate around and directly change the text we see. Pressing escape always exits a mode and it returns us back to the command mode, where we can then perform commands such as save, exit, or other commands we may wish to enter to manipulate the text. The V key enters visual mode, where you can do block highlighting manipulations of the text within. Again, when you need to exit the mode and return to command mode, simply press escape. When you're ready to exit a file, the colon key will be necessary from command mode to then save your changes or quit without saving. The most typical command we issue when we're ready to save and exit is the colon command to issue the commands, the letter W to write out our changes to the file, and Q to quit or exit the program. Once you've issued the commands you wish to enter, you'll press the Enter key to submit those commands. Let's open a text file and go through some of the exercises that we can do within Vim to learn the ropes. I'm currently logged into my user's home directory, and I'll create a simple file that we can use to make some interactions. I'll touch a file called text.txt. Now we can see we have our text.txt file located within our home directory. I'll use the command vim followed by the file name to enter the Vim editor. Once Vim opens this file, currently a blank file, we open in the command mode. Here we can use the colon key to issue various commands to interact with the contents of this file. Let's start by switching into the editor mode by pressing I or insert. Now we can type a sentence. When we're done editing the file, we can hit the escape key and you'll see that the insert at the bottom of the screen goes away. We're once again in our command mode. To issue a command to write out or save the changes, we can use the colon key, which you can see opens the cursor at the bottom, allowing us to now enter commands. If we simply want to save the file and not yet exit, we can use the W key to write that out. We type W and press enter. Now this file has been saved. If we wish to exit the file, we can hit the colon again and Q to exit or quit the file. Let's recall the command cat, which prints out the contents of the file or concatenates the contents to the screen, and let's do so with the file we just edited. Now we can see we opened the file, switched to the insert mode, added some content, saved our changes, and exited the file. There's a number of hotkeys that are available to us in the Vim editor, making it a very powerful modal editor. We've seen how we can insert text. We've seen how we could save and write our files out. Rearranging existing text, however, is also available to us, much like a copy-paste command. Let's take a look at that. Entering back into our text editor, using the command vim and the file name, we can see the original sentence we typed. By pressing the Y key, you can copy the line that the cursor is currently placed on. If you were to press the P key, it would paste a copy of this line. Y in this case is short for the command yank. P is short for the command paste. If we wish to delete a line that we accidentally pasted, the D key can provide that. Pressing D twice will remove the line. We still have this in our copy buffer, so we could hit P again and paste it directly back where we left it. The Y, P, and D keys allow us some helpful manipulation of copy pasting and deleting lines of text. Let's save our file with this new content by pressing the escape key to get out of the editor, colon key to issue a command, and X key. In this case, X is the same as W and Q. X is short for save and exit. We'll cat our file to see our changes. Visual mode is available for us to highlight and manipulate text. Three main keystrokes exist, which is the letter V to enter visual mode, capital V or Shift plus V to enter line mode, and Control plus V to enter block mode. Let's take a look at a simple visual mode interaction. Let's try out the visual mode in the Vim editor. We can use the various types of visual mode in order to remove or transform the text. Here, let's try using the block mode by pressing Control V, allowing us to block off all the characters we wish across multiple rows. Here I've highlighted both of the words now. We can then replace those by pressing R across both lines and then hitting the delete key to remove them. You can see how we're transforming all the text within the visual block at the same time. If we wanted to keep these changes, we could now hit X to exit the visual block mode, colon in order to issue the command, and then our write and quit arguments. If we take a look at the text we now have, we can see that the transformation is complete. That concludes our section on editing text files from the shell prompt. I'll see you in the next guided exercise where we have you follow along and put these skills to the test. Welcome back. In this guided exercise, we'll put our skills to the test and learn to edit files using Vim. First, we're requested to SSH over to the server A. I'll use the command SSH student at server A. Excellent. We can see we've now logged in with key-based authentication. Next, we're asked to launch the Vim tutor. Once launched, read the welcome screen and then perform lesson 1.1. To launch Vim tutor, simply type the word. It lets us know that we're about to perform exercises in order to learn the commands for Vim. Something it calls out very specifically is to ensure that your caps lock key is not depressed before you begin. Also, you can navigate the screen by using the J key to be sure that lesson 1.1 fills your screen. As I've got mine zoomed in much larger than you probably do by default, I may have some struggles and reduce that from time to time. All right, excellent. We can see here that the J, K, L, and H keys can be used for navigation. These 4 keys are all in a row, so you can learn to use them to navigate. These also serve the same purpose as the arrow keys, but there are many keyboards, especially older keyboards, that may not have those keys. Therefore, Vim has alternative ways to navigate around the environment. So they have asked us to move around to make sure we have this navigation. So press a combination of the J, K, L, and H keys until you get comfortable with each one's design. Continue to press the J key to move through the exercise. You can hold the J key in order to scroll faster. Now that we've completed lesson 1.1, let's go back to our instructions. The helpful hint here on how to remember what each key stands for here is the mnemonic phrase, hang back, jump down, kick up, and leap forward. That way the H key can help you remember that you go backwards on the line. The J key for jump down goes down a line. Kick up, the K key goes up a line, and leap forward leaps to the right or forward on the line. Next, we'll move into lesson 1.2. This will help you understand how to quit the editor without keeping any unwanted changes. The changes will all be lost, but sometimes if you're editing a critical file, you may want to simply back out if any erroneous information was accidentally entered. As instructed, make sure to read all steps before you perform any of them. Step 1 will have us press the escape key to make sure you're in the normal mode. You'll type :Q, ! And press enter in order to exit the editor, discard any changes you've made, and safely return to the command prompt. You'll get back to this location by executing the command that got you into the tutorial, which was Vim tutor, and pressing enter. If you have those steps memorized and you know what you're doing, go ahead and execute those steps. I'll do so now by pressing escape, :Q, ! And hitting enter. We've returned out of the tutorial. As instructed, we can retype Vim tutor to return to our work. Now that the Vim tutorial is open back up, we can arrow down or use the J key to return to our place. Lesson 1.3 shows that Vim has fast and efficient ways to navigate throughout words and lines of a document. We can use these to effectively delete an exact number of words or lines, sentences, or even whole paragraphs. We're asked to in step 1 to move the cursor to the line below, marked dot. Then, to fix the errors, move the cursor until it is on top of the character to be deleted. Press the X key to delete the unwanted character, and then repeat steps 2 through 4 until the sentence is correct. Let's go ahead and move to the end of the line. Now, we're asked to go ahead and use the X key over any erroneous characters. I'll delete this last O first, using the X key. We'll move over to one of the H's, either one, and hit the X key. Continue to proceed backwards over the line, eliminating the extra characters until you've fully corrected the sentence. Now that you've learned how to use the X key to delete single characters, let's proceed into lesson 1.4. Here, lesson 1.4 teaches us about text editing. We use the I key to enter into the insert text mode. Step 1 tells us to move the cursor to the first line below marked with the arrow. To make the first line the same as the second, move the cursor on top of the first character after where the text is to be inserted. You'll press I at that time and then type the additions, and as each character is fixed, press the escape key to return to normal mode. Repeat steps 2 through 4 until all of the updates are made. Here is the first line where there is some text missing from this line, as well as some characters. We'll want to arrow over while they're the same, and once we see some differences, we get to a point where we need to edit some text. We'll hit the I key to insert here and type some space. Now that we've corrected that part, we can hit escape to get out of editing and continue to move forward. Notice I'm putting the cursor where I need to have additions added after the cursor. Here I want to put additional characters after the first S. I'll hit I to enter the same mode. Let's continue to arrow over until we get to the next spot that needs correcting. Here we can see that some letters are missing from the word missing. We want to put the cursor exactly where we wish the characters to be inserted. Characters will be inserted between the S and the N if I press I in this position. I'll hit I to enter insert, type in the two missing characters, and hit escape to exit the insert mode. Here we know that we need to add an entire word from, so I'll align, hit I, type from in a space, and then hit escape to exit. The last piece should go over the period, hit I, type line, and we've now completed the editing that makes this line the same as the one below it. In this 1.5 lesson, we'll learn that keystrokes can be used to change the cursor placement when that text editing occurs. Here we'll use the capital A to append text. We'll move the cursor to the lines below, and it doesn't matter which character the cursor is on in that line. We'll press the capital A, Shift, and the A key, and type in the necessary additions. Once the text has been appended, press Escape to return to normal mode, and then perform all the work to correct these lines to make them identical before finishing the work. So here we can see that some text is missing from this line. There's also some missing from this line. So we'll move the cursor to the first line below as instructed. We'll press Shift and A to jump to the very end of the line and append what's missing from the end. We'll then hit Escape to go back to normal mode. We go down to the second line and we can hit Shift and A to jump to the end. We can say that there's also some text missing from this line. Now that we've added or appended text to the end of the line, we can see the value of that the capital A gives us when we need to append content to the ends of lines. There is also some text missing here. I was able to use the insert and then my backspace to delete the keys that I had accidentally put in place. Teaches us that the W and Q commands will allow us to write and quit the files. We've already seen this, but let's go ahead and reinforce it by writing out and saving our changes to this file. If you did lesson 1.2, you can quit and use the exclamation point to force the exit without saving changes. If you like what you changed and you wish to change to exit out and save your changes, you'll use the :WQ command. I believe we did a great job writing out all of this, correctly completing all of this work, so we'll write out and save our work. So escape, :W to write out our work, Q to quit. Now, as instructed, let's retype Vim Tutor and proceed to the Lesson 1 summary located at the bottom of the experience. I'm using J to hold all the way down to the Lesson 1 summary. To summarize what we learned, H is used in tandem with the left key, J for down, K for up, and L for right movement. We can start Vim by typing Vim in a file name in order to launch the editor. And we can exit Vim a few ways that we've learned. Using the Q or Q exclamation point to exit without saving changes, and using the WQ command in order to save changes and exit. When we're in normal mode, we can use the X key to delete a single file a single character located under the cursor. And then we learned how to enter insert mode using I at the place of our cursor or capital A for at the end of the line we're currently on. The escape key will always return us back to normal mode, and then we can feel comfortable saving or exiting the file as we see fit. I hope you enjoyed this guided exercise on editing files using Vim. I look forward to seeing you in the next video. In this section, we'll introduce the concepts of user and group management. When working in computer systems, it's really common to utilize user and group management. In Linux, it's no different. A user account is available to provide security and boundaries for a particular user who User accounts in Linux are used to provide unique credentials and provide security boundaries between the various users on the system. Each user will have a unique username as well as a user ID number that the operating system manages. This will then be coupled with access to various parts of the operating system itself and managed throughout complex permissions that are available. Each user ID or UID must be unique throughout the system. This will correspond to the various access that they have throughout files and folders. We have three main types of users when it comes to Linux. We have a super user, a system user, and regular users. The purpose of the super user account is for administrative purposes. By default, the super user account is known as root. The root user is stored in the UID 0. This user or super user has full access to the entire system. The next type of user is a system user. System users are responsible for running the processes throughout the operating system. You could think of these as managed by the kernel or the operating system itself because they're used to launch the various processes that make our experiences happen. The processes, or daemons, that run consistently throughout the operating system don't need to run with all of the administrative privileges that the super user has, and instead are run as system users with the proper delegated authorities that the particular application or process require. Our most common type of user is just a regular user. This is one that you would use in your day-to-day work and would be coupled with a username and password so that you can access the files and systems you need within your Linux operating system. When you need to view information about a specific user that you're logged in with, you can use the ID command. Here you can see a sample output of the ID command when logged in as a sample user, in this case, user01. We can see that the UID information is given, in this case, with the UID 1000 coupled with that username. There's a group ID generated as well. Here the GID is 1000 that corresponds with a group named user01 as well. When we create regular users, a corresponding group of the same name is also created. Lastly, we can see any groups that they may be a member of listed out. The context is used with SE Linux environments in order to provide an enhanced layer of security. If you wish to view information about a different user, you'll just simply adapt the same command to include the username you're trying to inspect. We've already been seeing user information about the files we've interacted with from time to time. Using the ls-l command, we get the long listing details of a specific file. Here you can see the user01 has issued the command ls-l on a particular file in their file system. The output will correspond to the permissions for the file. We'll learn more about that later. And here we see the user that currently owns this file. While this may be getting a little ahead, we follow that with the group information as well, followed by specific information about date and timestamps for the file itself. You can see an additional output for a specific directory. Using ls-ld on a directory will tell us 1, this first character in the permissions field is a directory, and 2, who owns it for both the user and group. When it comes to inspecting processes, and particularly as it relates to the system users who run them, we can use the ps command. The ps command, coupled with several flags, can be a very powerful tool in a system administrator's toolkit. Here you can see we're using the command ps-au. The A option in this case allows us to view all processes within the terminal. When we wish to see the user that's executed those processes, the -u option provides that information. Have a look inside this example output of the ps command. You can see in the user column the various users that may be running the specific process. It's not uncommon to have a process run as the super user root. However, it's not required unless specifically instructed to do so. While the PS output shows us the names of the users who run these processes, each username is mapped to a user ID or UID for the system. It's actually these UID numbers that are used by the operating system in order to keep track of the user management itself. Usernames are actually just simpler ways for us as humans to know who we are. The operating itself relies more on the numerical values of the UID. The etc password file, which we've inspected previously when learning our first commands on the command line, does include one line per user. When you inspect the etc password file, you can see a lot of information about the users contained within your environment. This will include all types of users. We see here some example output of one line contained within the etc password file. Let's understand what each of these fields means for us. The first field is the username itself. This is the human-readable form of the username that we are very familiar with. In this case, the username is user01. The second field typically holds only the value X. In a less secure world many years ago, the plain text password was stored here. We can now understand that storing plain text passwords is not a proper behavior, so we have this placeholder here denoting that the encrypted format of the file is stored elsewhere in the file system. Namely, there's an etc shadow file that contains this hashed salted information. Next, the third field shows the number 1000 in our output. This number 1000 is the user identification number for the user01. This is the numerical value that the operating system will utilize when assigning file ownership or assessing valid access when user01 tries to manipulate anything throughout the operating system. The next field is the group ID. A group ID is associated to a group name, much like a user ID is associated to a username. The operating system keeps track of group membership and ownership using these numerical values. In this case, the number contained in the GID field relates to the user account's primary group. Here it's shown as the number 1000. We could inspect the file etc group to see a list of all files and their members and understand the relationship between group ID 1000 and the group name of that is associated with that GID. It's typically safe to expect that a user would have its primary group of the same name, which gets created when we create users, but this isn't required. To know exactly which primary group your user belongs to as in this field, you would need to cross-reference this information with the corresponding numerical GID and etc group. Field 5 is the real name for the user. In this case, they've typed out user1. This is just helpful human-readable text to describe the user who is intended here. It's most common in organizations to put someone's full-length name in this field, while their username may be some degree of abbreviated or even unrelated word. Number 6, or field 6. Field 6 shows the user's home directory. When a user logs into the environment, even remotely or locally, and opens a terminal, this would be the location that user's shell is currently working from. The last field here shows the value bin bash. This is the shell value. When a user with this account logs in, the particular shell that will be presented when they open a terminal or establish a remote connection can be changed here. By default, we use the bash shell. If it was a system user, however, that we didn't wish to have login access remotely, as that would be a bit inappropriate and even unsecure, we can use the phrase sbin no login, meaning that there's no login interactive shell for that user. A group allows a logical collection of users so that they can have similar access to files and folders. Groups are used for group ownership of every file within our operating system and then allows for the assessment of access based on the permissions set at a group level. Each group has a human-readable name that we use to interact with it, but always maps to a group identification number, or GID, in the same way that we saw users map to their user IDs. The operating system itself will actually keep track of group ownership, and group membership via these GID numbers. By default, the system will use the file located in etc group to store this information. Here is some sample output from the etc group file. This is an extracted single line from the entries in etc group. Let's take a look at what all the values mean for each of these fields. First, we see group 01. This is the group name. Many groups exist within the etc group file itself, and each one has all of the rest of its characteristics described in its entry. Field 2 is an obsolete field that included a group password. If group passwords are enabled and utilized, that information is now stored elsewhere. Originally, this would have been stored in plain text here, but we understand now the security implications of keeping and managing data in this way. The next field is the group identification number, or GID, here shown as 10,000. The GID number, remember, is how the operating system actually keeps track of groups, group membership, and group permissions. Lastly, field forward lists all the users who've been added to this group. This is members who've added this group as a supplementary group. We saw in the user identification area of Etsy Password that a primary group is assigned to each user. Group membership, done in that fashion through the UID's primary group, is not going to show up as a list here. Only membership in supplementary groups are shown in this fashion. Here, we know user 01's primary group was a different group, namely GID 1000. This group, group 01, is a secondary or supplementary group for that user, and therefore the user shows up as an added member to this group. In this section, we'll explore gaining super user access. Once we're done, you should feel comfortable being able to use the sudo or sudo command. This will allow you to access the privileges of the super user from a normal user account. First, let's discuss the super user. Most operating systems have some concept of an administrative or full access user account. In Linux, we call this the super user, and by default, that username is root, R-O-O-T. The root user has full access to the entire operating system and can override the changes of any other user. It's important when you create Linux accounts to know that this user exists for both the senior administrative tasks required throughout the operating system, as well as to understand the powers granted when someone has access to this account. The root user account should be reserved for only administrative purposes, and being able to access this account should be reserved for only people who need that access. Root passwords should be set and secured in the highest of fashion. Many administrative tasks that we do on a routine daily basis do require this type of access. Installing or altering software, adding or removing USB hard drives, as well as many other just files and configuration settings throughout the operating system will require these elevated privileges. It's not uncommon to use the root account for many of the work you'll do in Linux. However, with great power comes great responsibility. Be sure to secure this account with strong passwords and limit who has access to the account to only those who will perform those elevated responsibilities. If you're coming from a Microsoft world, the root user account and super user privileges in Linux are akin to the administrator account within a Microsoft Windows environment. It's very common to need to switch between one user account and another. It's even common to need to elevate those privileges to the super user account. The first way we have to do that is with the SU account, or switch user. We can use this command to switch between any user accounts that we have access to. If we try to switch to another user, it'll require us to enter the password for that other user using the SU command. If you want to switch from the regular user to the root user, it'll require you to have the root user's permission in the form of a password. If you're required to enter a password for the switch you're making, the password prompt will appear. Recall that when you enter passwords in Linux, the cursor neither moves nor displays the characters you're typing. Here, I see that I'm the student user. On my account, I have also created a demo user. We'll learn how to do that soon. If I wish to switch between users, I can type su switch user command and then the other user account I wish to switch to, at which point the demo password must be supplied in order to switch users. I'll type that password now, and we can see some error messages that occur for the demo user, but we've correctly switched to that user. I can type exit to return to my original user. Note that when we use the su command and do not declare a specific user, by default it will switch to the root user. If you have access to that account and have the password, you can supply the root password at that point in time in order to switch to the root super user account. We see in the output here that they're using the SU followed by a minus sign or dash. The difference here is that when you use SU dash, it'll start as the new user with a login shell. The login shell declared in their entry of Etsy password. Including the minus sign will set up the shell according to that user's environment. If you omit the minus sign or dash, SU just starts the simple shell that the user was already using, but with the new user account logged in. Feel free to experiment between switching between users using the minus sign or omitting it. In this section, we'll look at running commands with the sudo argument. Many times, we have access to the root account as system administrators. However, it can be more secure to allow access to root privileges without handing out the password to the root user. We can do this by configuring our users with sudo access. Sudo is short for super user do. I can prepend it to any command that requires super user privileges and execute it as my own user. If my own user has been configured with this access, I'll then supply my own password and execute the command with the elevated privileges. This allows me system administrative access for commands and areas of the operating system that are outside of my regular user's access, but if I've been granted that super user privilege, I can then do so by supplying my own password. This keeps an environment secure because then no one with this access who requires those elevated permissions actually knows the root user's password. If you were to have the root user compromised or the individual user's account compromised, you can mitigate this far easier. Editing the etc password file as a regular user is not something that's allowed. We can try as our student user to edit etc password. The file is able to open up. I'll enter the insert mode by pressing I. Notice that I do get a warning message that says I am changing a read-only file. This is because the user I'm currently interacting with, the student user, does not have permissions to edit this file and save changes. Any changes I were to make would be lost when I exit the file. I'll exit the file and quit without saving any changes. Next, let's try prepending this with the sudo argument. Here I'm asking it to interact with the file with elevated root level permissions. As my user is configured to be able to do so without entering a password, I immediately enter into this file. If I hit the insert key and start typing, anything I type in is allowed, as I'm now doing so as the root user. This can be very dangerous, especially in the etc password file, as this file governs all user access. Be careful with the files you interact with using these permissions, as you can do irreparable harm to your environment. I'll exit, and I will not save my changes in this case. Just know that using the sudo command to do so would have allowed me full access to edit the file. You can see some further examples in the book that show using the sudo command to access areas of the file system that are not normally allowed for regular users. Within later versions of Red Hat Enterprise Linux, members of the wheel group can use this sudo privilege. That's actually the configuration that's in place in my environment to allow my student user access to the account root. We can see in etc group the configuration of this group. If we open the file etc group for editing, we can arrow down and see the group wheel. Here, both my student and demo account have been added to the wheel group, meaning that they've been extended privileges to use the sudo command and gain the super user elevated privileges. I'll exit out of this and I'll show one other area. The command vi sudo allows you to access the configuration file for these sudo privileges. Notice as a regular user, I don't have permission to run this command. If I add sudo to the command, I'm asking to do this as the super user, and I should be able to gain access to editing the file. Arrow down until I see the wheel group configuration. Here we can see several options on how the wheel group gets configured. The hash sign or pound sign shows configuration settings that are commented out. We can see that this line here does not have a comment and is the active configuration for the wheel group. While this may not be obvious to you as new Linux users, this line says that all members of the wheel group have access to all commands and do not require an entry of a password to use them. I do not recommend these settings in a production environment, but we use these in our learning environments to make it easier for users to interact and try out the sudo access. Oftentimes, we do want to actually switch to the root user. With the sudo command, we can do this as well. As a user, I may not have been given the root password, but if I've been extended sudo privileges, one of the things I can do is use sudo to switch to the root user. This will allow me full administrative control of everything in the file system with my new elevated privileges. We can see the command sudo su dash would ask for us to invoke our sudo privileges to switch users and load the root user's environmental shell. Let's do that in a terminal. Here, I'll give it a try. Sudo su dash. As the super user, switch users to the root user. As I'm configured to allow sudo access without passwords, I'm not prompted for my password in this environment, but I have successfully switched to the root user. You can also see that my current working directory has changed to load the environmental home directory of the root user, the directory /root. That concludes our section on the super user access. Join us in our next video to follow along in a guided exercise with these skills. Welcome back to our guided exercise on running commands as root. Here we'll test your ability and walk you through the steps necessary in order to become the root user and execute commands with the super user privileges. Step 1 has us explore the characteristics of our shell environment. We'll do so with a few commands, the first being the id command. Alright, great. And the next one is the pwd to see our current working directory. Now we want to take a look at a few of the environmental variables available in our environment, namely the home and path variables. So by default, the echo command on $home should match the home directory for the user. This, when you say cd tilde, the shortcut we learned previously, this is how the environment knows where to change directories to. Next, we're going to echo $path. Your path is unique to your user in the sense that it includes localized directories. You can see from left to right in the output of this command, it's getting less specific or more general in the environment. First, from your home directories, hidden files for local binaries, all the way up to your binaries, and then you get into more and more general locations in the environment, all the way out to the /bin or binary directory. These binaries are the locations of the commands that you want to run in your environment. When you type a command, if it doesn't exist in one of these locations for the actual files that provide the instruction set for that command, then the command won't be found or won't execute properly. So altering your path as you include more directories in a more advanced phase of your Linux career will allow you to run commands out of some custom directories. These variables can be updated, certainly, as you see fit. And, at this point in time, we're just learning how to inspect them and start understanding what they're for, but each holds a purpose. Now, we want to switch to the root user. We're going to use sudo to run the su, but we're not going to use the dash. Here, that means that we're not going to load the new shell environment for the root user. So we're just going to run sudo su. Okay, it's asked for the password for the current user, whatever you set your password to. We did not include the dash, remember? And now we're asked to inspect this environment. So here we'll use the id and pwd, the echo commands again, for home and path. So do id, and then pwd. Notice we didn't change a directory here because it didn't run through those variables, but we are going to echo $home. See, the home directory for the root user is /root, and we're not in that current directory, so it didn't, execute us into that environment with that. And then if we echo $path, we can see the root user's pathing. All right, now we're asked to drop back down to our EC2 users, so let's exit. Okay, I'm going to clear the screen, and I'll just do a who am I so you can see that I am the EC2 user once again. Now we want to run sudo su with the dash to become root, and we'll take a look at some of that information again. All right, so do an ID. Okay, that looks good. pwd, see, we did get switched into our root user's home directory of /root. And if we echo $home and echo $path, that information looks correct. And now the path information may vary in your environment. It's localized to the way that you installed or which version of Linux you're running. So if the path is different, don't be alarmed. The note here to take away is that we do not have the directories that are included in the EC2 user. We've actually switched to a path specific to the root user. All right, now we're asked to exit out this root login again, so let's go ahead and do that. And I like to clear my screen, show you a who am I, just so you know I'm back to that EC2 user. Now we're asked to run a few commands that require root access. Rather than using sudo su dash to become root, we just want to run them as sudo, meaning as the super user do. The example we have here is to interact with a file var log messages, a file that contains system messages in a log. And we're asked to interact with it first without privileged access, and secondly, using the sudo command in order to access that, because it does require super user access to interact with these files. So tail -n, and we just want the last 5 lines of var log messages. Okay, we can see that we encounter a permission denied. So if we just up arrow and do a sudo, we can see we then are able to interact with the file. Now, your results on the output may vary simply because your messages log may have different information in it. But the fact remains that you can only interact with this with the proper super user permissions that we're invoking with the sudo argument. All right, now we want to copy etc issue into etc issue old, and we'll do so with just a simple command. Let's cp etc issue to etc issue, and we're just going to tack an old on there. So now we can go ahead and try again with our sudo privileges, super user do. And sure enough, we can ls etc. We can just do like a file on etc issue old and see that it exists. Perfect. Now we want to remove it, so let's just try a remove command. Let's do rm etc issue old. Yes, we want to remove. Oh, but we can't because we don't have privileges. Again, sudo is your friend, and the file is gone. I'll do a file etc issue. Now, it should have tab completed to give me the option of issue old. It's not there. I'll explicitly state file etc issue old, and it says no such file exists. Great. Now you can see the difference of running commands with and without the super user permissions. The sudo command in particular allows you to invoke these permissions without actually changing users. This can be quite valuable, especially in an environment where you wish to extend those privileges to someone but don't necessarily want to share a root password with. This is a really good security implementation that Linux extends to users to allow that super user escalation without actually having the password itself, allowing control to those privileges to remain at the top level administrator's, realm of responsibility. That concludes this guided exercise, and I look forward to seeing you in our next videos. I'll see you there. Our purpose here is to make sure you're equipped with the tools necessary to create, modify, or delete local user accounts. When we start managing local users, 3 main commands exist. The user add command adds new users. We have user mod, which can help us modify existing users, and user del, which deletes users from the local machine. The basic syntax of a user add command simply requires you to supply the username that you wish to create. If you type user add -- help, you'll also see the entire list of options available through this command. These options allow you to specify further details about a user during creation. In this fashion, you could supply a different or custom home directory or UID if it were appropriate for your user in this case. When we have existing users that we wish to update or alter, we can use the user mod command. The user mod command has its own -- help, which supplies similar arguments to allow us to manipulate the individual fields and values for a configured existing user account. Have a look at the table that supplies the options for these previous accounts. This will serve as a great reference as you start learning the user commands. When we wish to update various fields that we find in the etc password file that correspond with a user, we have a flag or option for each of these commands in order to manipulate that specific data. If we wanted to alter a group's UID, shell, home directory, or group ID, a corresponding option exists in order to supply that information. Here you can see things like the -c or -- comment option, which allows us to update the field for the comment section. This typically includes a username's actual real-life name. A common use for this field is to supply the real name that corresponds to a user account. We can see additional options in order to move the home directory from its default location, or even alter the shell with which a user logs in. I'll call out most explicitly the bottom option. The bottom option in this case is the -L or --lock argument. This will lock a user account, meaning that user can no longer log in locally or remotely with their credentials. This can be a good option when you need to disable an account for a short period of time, but do not wish to delete the user account entirely. In order to unlock an account, we simply need to understand that the -U option would provide us an unlock argument. If a user needs to resume a locked account, you'll need to go through the steps to unlock it before it can proceed. The user del command is used to delete users that we have within our system. It takes an argument of just the username we wish to delete. One key flag, though, exists, which is the -R command. -R command will also remove any of the files in the user's home directory, as well as the directory itself. When we wish to fully purge the documents and contents of a user's home directory when we remove the user, the -R option will be required. When we use the command passwd and supply a username, we're then allowed to change the password configured for that user account. If we do not supply a username when we pass in this command, it will assume that you wish to change the password for the current account that you're utilizing. In general, a user can only change their own password. However, given the powers of Sudo or the ability to log in with root permissions in general, you can manage and manipulate the passwords for any user account. When we invoke a password change, you can see a simulated interaction in the box below. This box shows the command password being used to update the password for the user 01 account. Initially, you're asked to enter a new password. This will only be the case if you're using the root user. By default, with any other user, you'll be required to enter the current password for that user and then supply the new password. Since this example output is being done as the super user is the only user who can omit entering the initial password in order to invoke a change. This makes sense as the administrative user has the privilege to reset passwords for any user. Each user has a unique user identification number. These UID numbers have specific meanings based on the ranges that are assigned throughout the operating system. The root or super user account will always be assigned UID 0. UIDs 1 through 200 are reserved for system users, or the users that will be required to run specific applications and processes. The particular system users in the range of 1 through 200 are the ones that are statically assigned by Red Hat. The system user ID range from 201 to 999 are system users assigned by their own applications and processes. These are not typically statically assigned or reserved, but may be different across various operating systems. Programs that execute in these ways will run as their own user ID and be configured through the installation of the software that they run to have the proper and appropriate permissions throughout the file system. User IDs 1000 and above are available for regular users. As we add our own users, they should iterate through the values above 1000. That concludes our section on managing local users. Much like our last section, it'll be important as a system administrator to know how to manage local group accounts. We'll learn the commands that allow us to do so. Groups must exist prior to a user being added to the group. We will take a look at the command line tools available to you to create and manage these groups as well as the membership of users within. The first command that we'd like to take a look at is the group add command. As expected, the group add command allows us to create new user groups. If we supply no further options, the group add command will simply create the group of the name that we designate. We can additionally supply further options such as the -G option if we wish to specifically declare a group ID for this use. You can see an example of this approach being used in this output. Here, we're using the group add command, the -G flag, and the GID of 10,000 to create a new group called Group 1. When using the group add command, there's also the -R option. The -R option will create a system group using a GID from a range of valid system GIDs. These are defined in the file etsylogin.defs. In general, this allows us to conform to a standard convention of reserving GIDs 0 through 999 as system groups. You can see the example output here of a system group being created with a GID in the appropriate range. Here, the group add command passes the -r option for group 02. We can see that group 02 receives a GID of 988 within that 0 through 999 range reserved for system groups. When we wish to modify the settings for a specifically created group, we have the group mod option. The -n option for group mod will allow you to rename the group. Here, you can see an example of the group mod -n option renaming group 022 to group 02. The -g option will allow you to specify a new GID, and you can see an example output here of reassigning the GID to 20,000 for group 0022. By inspecting the file etc group, you can see that information is updated. The last new command we'll look at is the group del command, allowing us to delete groups. Here you can see a simple interaction using a sudo command to delete the group 022 using the group del command. A word of caution exists that you cannot remove a group if a user belongs to it as a primary group. In other words, in etc password, if a user has the primary group declared, that group cannot be deleted until this information is updated. When we wish to manage group memberships in this way, we have the user mod command and can pass in both the -g or G arguments, depending on whether we want to update people's primary group or secondary group memberships. The -g will allow us to update the primary group for a user. Here we can see the user 02, and the output of the ID command for that user. The output of that command shows that the primary GID for this user is this group here, or the user 02 group. If we were to execute a user mod statement to update that to the user 02 from the user 02 group to the group 01, we could then inspect the ID of user 02 again and see the updated GID. When we use user mod and the -a G flag, we will then be able to add additional secondary groups to the user's configuration. The -a argument allows us to append further groups. Without the -a argument, the list of groups supplied by the command would replace any group memberships the user has for supplementary groups. By using the A, we're allowed to simply list out the groups we wish to add as well as the ones they currently belong to. In the output below, you can see an interaction using the user mod command and the -a G interaction. These arguments allow us to update and add to additional groups the user 03. We can see from the output of the initial ID of user 03 that this user belongs to the groups 1009 or user 03. When we add the secondary group 01 to this user and then ID the user again, we see that they have the initial user 03 as well as the new group 01. This concludes our section, our guided exercise on managing groups using command line tools. Here we'll simulate what we did with our users, but we'll do the group side this time. Let's go ahead and dive in once you're logged in. We'll begin by becoming the root user. Now that we're the root user, we're going to add a group named Shakespeare and assign the group ID of 30,000. We'll assign the group ID with the lowercase g option. And the group name was Shakespeare. Now, just to show you where that lands, I'll just tail dash in one etc group. Great, so we can see we've got our group in place now. Now we want to create a new group named Artists. Simple enough, no other specifications, so that's just a simple group add. Artists. We can just run our tail command again and see that that's just showing the last line of the file. In etc group, I can go ahead and expand that. Let's take a look at the last 5. We can see some of our last users we created got their own group created that matches the username, and then the 2 new groups we just created. Now we want to add Juliet user to the Shakespeare group as a supplementary group. That's a G option. So we'll do a user mod on that. User mod -G Shakespeare to the user Juliet. And then we can run an ID command on Juliet to see that her group when we see the groups here, include Shakespeare. And we can see that matching GID or group identification number. Now, these are her secondary groups. Oh, don't highlight the whole line. Secondary groups here, whereas the primary group is always shown by the GID that it's assigned to. So our primary group remains the Juliet group. Now we want to continue adding the remaining users to groups as follows. We want Romeo and Hamlet added to the Shakespeare group. It doesn't explicitly say, but by the command we can see that's just a secondary. So that's a simple user mod command. It's the same thing here. So Hamlet, I think I did them in backwards order here, but Romeo, and then that should be fine. We can do an ID on Romeo and an ID on Hamlet just to verify that work. Looks good to me. I'll clean up here. Now we want to put Sunny Huang and Jerlene into the artists group, secondary, supplementary group again. So now it's user mod dash capital G artists. And we said Sunny, and we said Huang, and we said Jerlene. Okay, and we can ID Sunny, ID Huang, and ID Jerlene. Great, we can see that all of them have been added to the artist group as a supplementary group. Now we can just tail the Etsy group file to see these additions as well, because they'll be explicitly listed there. So let's just tail dash in to Etsy group to just see those last two groups. Shakespeare has Juliet, Hamlet, and Romeo. Notice they're added in the order I ran the command, so your Romeo and Hamlet may be switched. Artists have the three users, Sunny Huang and Jerlene. I hope you feel a little more comfortable managing groups from the command line and then managing users as members of those groups. That concludes this guided exercise, and I look forward to seeing you in our next section. Welcome back to the lab we have on managing local Linux users and groups. Step 1 asked us to create a new group named Consultants assigning a GID of 40,000. Since we need to be root to do this work, I'll use a sudo command. Optionally, you could switch to the user. We're asked to add the group with a specific GID. We use the lowercase g option to do so. The GID we were asked to supply was 40,000. We'll end the arguments with the name of the group, Consultants. To make sure that this group exists, we'll just take a look at the last entry in Etsy group. Great, we can see our group exists and the GID matches what we were asked to set. We want to create 3 new users and add them to the consultants group as a supplementary group. In order to specify a supplementary group from a user add argument, use the capital G. If you create these users individually and then want to add them after, you'll use a user mod command of the same fashion. I'll try to do this work in single commands. And then D. Jonathan. Yeah. And once I do that once, I can just up arrow and erase the username, and then Liz, up arrow, and then D. Tyson. Okay, now let's take a look at that group one more time. Oh, well. Now we have a bunch more groups added, so it's not just that last one. So let's just look at the last 5. And we can see we have the consultants group, 40,000, with these 3 new users. Now I'm asked to create passwords for each of these. So let me go ahead and do a sudo password argument on each of these users. Sudo password, D. Jonathan. And I'm setting secure passwords here. Not secure enough to omit the argument, but something a little healthier than just matching the usernames. Okay, I'm going to clear my screen, and I've created the passwords for each of these. Now we just want to check each user to confirm it exists and has the group memberships we expect, and specifically we're looking for not only the GID that matches the username, but the supplementary group for consultants matching GID 40,000. So let's do an ID Okay, that one looks good. Oh. Okay, this looks great. All of them have the 40,000 consultants supplementary group and remain in their own primary group. So that was as specified. That concludes this lab, and I look forward to seeing you in our next chapter. Keep those thinking caps on. We're going to keep that learning going. To complete this section, you should be familiar with how to display and interpret the permissions set on the files throughout the file system. File permissions are in place to control access of who has what to various parts of the directories and files throughout the operating system. We'll want to make sure that we keep things as secure as possible, but we never want to inhibit appropriate system interactions, and the application permissions allow us to do exactly that. There's three main categories in which files have a permission set on them. The first is the file's owner, or the username that's associated with ownership of the file. The second is the group owner, or group name associated with the file's ownership. And lastly is everyone else, or other. More precisely, everyone else or other is neither the username that owns the file or any of the members of the group. We shortcut these abbreviations to U for user, G for group, and O for other. When a user falls into more than one of these categories, the most specific designation takes precedence. For example, if you're a member of the group that owns it, that would be your most significant precedence. If you were also the user who owns that file, the user permissions would override the group membership. Have a look at this diagram. In this diagram, we have two users, Joshua and Allison. Allison belongs to the Allison group as well as the Wheel group, while Joshua belongs to only the Joshua group. A group named Web can be created, and both Joshua and Allison can be added to this group. This would allow a collaborative way to have files owned by the Web group allow access to both the Joshua and Allison user for access. In this way, you can design out the groups added to your environment and supply the members into each of those groups that facilitate the workloads required in your own environment. As we go forward, we'll take a look at some of these permissions, but before we do, we need to understand what the specific permissions are and what each permission means when it's applied on a file or directory. The first permission to discuss is the R permission for read. When we're talking about a file itself, that means that the contents of the file can be read or displayed to the screen. When we're talking about a directory, that means that we can list out the contents of the directory or the file names contained within that directory. The next permission is W. This is short for the write option. When a file has the W permission for your particular access, that means that the file contents can be changed by this user. When we're talking about the write permission on directories, that means that any file in the directory can be created or deleted from that location. The last permission is X for execute. When this is for a file, that means that the file can be executed within commands. This should be reserved for only files you intend to have executed output within the environment. When we supply the X argument or X permission to directories, that means that the directory can become your current working directory, which means that you're allowed to use the cd command to change into it, but also it will require the read permission to list files found there. It's not uncommon for a user to have both read and execute permissions to read-only directories. This allows them to view the contents of the file and execute it if it's a script of some sort or a command. Extending the write permission may not be appropriate in those instances and is oftentimes omitted. Files and directories may be removed and altered by anyone that has the proper permissions to write in those locations. It's always important to assess who has write privileges in your files and directories to make sure that only those who have appropriate access are properly set up. We do have a special permission, known as the sticky bit, which will allow us to override this behavior, but we'll discuss that a bit later. We'll take a look at viewing file and directory permissions and ownership. We'll want to be sure you know how to display and read these entries. When viewing file and directory permissions and ownership, we can use a number of commands and their options and flags to do so. The main command we'll use for this is the ls or list command. When we've done long listings using the -l option, we've seen a lot of additional information that we glossed over at the time. Now let's take a look a little more closely at the beginning part of a long listed entry to understand the permissions that may be set in that location. When I do a long listing on my home directory as the student user, I can see a number of directories and files. Here we can see that directories have a permission block that begins with D to denote its purpose as a directory. The remaining bits are the permissions for user, group, and other. Here we see a directory that has read, write, and execute privileges for the user. How do we know who the user is? It's declared here. Next, we have the read and execute permissions, but not the write permissions for the group, declared here. Lastly, we have read and execute permissions declared for the other or everyone else. Anyone who is neither the student user or belongs to a group named student would inherit these permissions. So in this way, we configure our permissions in 3 sets of 3s. The first 3 permissions, read, write, and execute, either on or off for the user. The second set of 3 permissions, read, write, and execute for the group. And the third set of permissions, read, write, and execute for other. Enabling and disabling each of these flags allows us to granularly control the access that users, the owning group, and everyone else have to these files and directories. Several specific file types use the first bit to denote what kind of file they are. We can see here the list of characters used to denote what kind of file each one is. A regular file will begin with a simple dash. A directory will begin with the letter D. Links, specifically soft links, will begin with the letter L. And other characters that represent hardware devices such as B and C, or special purpose files such as P and S, exist. We then saw that the next 9 fields are used to denote the file permissions in sets of 3. The first 3 for the user, the second 3 for the group, and the third 3 for other. In a hypothetical scenario, let's consider that we have users and groups configured in this way. User operator 1 belongs to several groups shown in this table. The operator 1 group of the matching name, as well as consultant 1 group. Database 1 user belongs to their own group and the consultant 1 group. Database 2 user belongs to their own group and operator 2's group. And then contractor 1 belongs to the contractor 1 group and operator 2 group. We can take a look at this output to start considering some of the permissions that we see. Have a glance at this output as we discuss these permissions. Specifically, our permissions will always occur in the boxes here. Taking a look at the first file, we see that we have the local directory, or dot, the current working directory, set up as a directory with RW and X, or all permissions, for the user, database 1, that owns the directory. We see that we have RW and X for the second 3 permissions for the group consultant 1 that owns this directory. And lastly, everyone else will inherit read and execute permissions if they're neither the database 1 user or a member of the consultant 1 group. Having a look at another file in this listing, we can discuss the permissions set there. Here we can see a regular file with user permissions for the operator 1 user set to read and write. This means that they'll be able to both view and modify the file, but cannot execute it as that permission is not granted. Members of the group consultant 1 will be able to read only the file. And lastly, anyone that is neither the operator 1 user or a member of consultant 1's group would be able to read and write within this file. The file in question is named lfile2. This concludes our section on the examples of permissions effects. When learning how to manage the permissions for files and directories in the file system, one main command comes to mind. The command chmod is used to change the mode or permission bits for any given file or directory. It's called change mode because we refer to the permission expression that we've seen previously with the 3 groups of 3 as the mode bits of a particular file. When we change the mode, we're referring to changing the mode bits or permission bits set on each file and directory. There's a few ways we can use the chmod command in order to change the permissions on a file or directory. First, there's the concept of changing permissions with the symbolic method. When we use the symbolic method, we use the letters U, G, and O for the user, group, and other permissions. We also have shorthand for A or all when we need to change all these bits at the same time. We then use the plus, minus, and equals to either add, remove, or exactly specify the permissions we wish to enable. And lastly, we use R, W, and X, the read, write, and execute permissions we recently reviewed. When we wish to use the symbolic method of permission management and the chmod command to do so, we combined the UGOA, the symbol of plus, minus, and equals, and the permissions RW and X as fit for the files we wish to manage. A properly formed command would take the form shown here. We would start with the chmod command, name what we wish to alter in the permission form using the syntax who, what, and which. Who corresponding to the user, group, other, or all. What corresponding to adding, removing, or exactly setting the permissions that are which are W and X, read, write, and execute. In that fashion, we can begin to form permission statements that look something like the following. In our first example, we're using a chmod statement. Let's dissect this statement to understand exactly what's going on in the permissions here. We're using chmod to change the mode bits for group and other, G for group, O for other. A minus sign means that we're removing permissions, R and W, read and write, for the file 1. In this case, read and write access to file 1 for the group members as well as all others would be removed. In the next example, we're adding execution permissions for everyone on file 2. In this way, we'll use the chmod key A to say for all, group, user, and other. We're going to use the plus symbol for an additional permission, and we're going to add the execute permission to everyone. This means that everyone should have execute privileges for the file specified, file 2. That's the first way that we can manage our permissions, but there's also a numerical way to manage our permissions. When we start learning numerical work with our permissions, we need to understand how to express the 3 values for R, W, and X bits being set on and off in an octal expression. Let's start with a quick look at what binary and octal representation means in this case. Let's go ahead and start working with our permissions and assigning them numerical values. Let's start by understanding we have users, group, and other. Each of these will receive one or more of the 3 permissions: read, write, and execute. We'll go ahead and draw a little line here and a line here to collect our work. Now, let's start trying to iterate what some of these would look like. If we want our user to have read and write permissions, our group to have read permissions, and no one else to have permissions, we could fill out the graph as such and express the resulting permission as R, W, dash. For group, we would have R, dash, dash. And since the other has 0 permissions, it would be 3 dash. It's in this fashion that we can begin understanding the binary then octal representation of these particular permissions. I'm going to draw a line between user and group and other. Here we now have begun to start understanding that we have 3 sets of 3. I'll now convert each one to a 1 where they have the permission or a 0 where they do not. I'll use a separate color to make sure we can keep our work separate. Here we have a 1 because the read bit is enabled, a 1 where the write bit is enabled, and a 0 where the execute bit is not enabled. Here we have a 1 for the read bit and a 0 for the other bits. Lastly, we have none of these permissions for other, so therefore we have 3 zeros. So that we can keep this straight, I'll go ahead and label at the top that this is user, group, and other. At this point, we've taken our intended setup of permissions for user, group, and other, corresponding to the read, write, and execute permissions, written them out as we would see them on the displayed permissions output of an ls-l command, and now converted them to on and off switches in the form of binary. Now, binary math is not native to everyone. However, this is where we get the translation from our binary to what is known as octal representation. Binary has 2 digits, 0 and 1, while octal has 8 digits, 0 through 7. We can go ahead and refer to binary to octal conversions to understand that 110 in binary is actually a different number, a single digit in octal. That digit in octal is 6. 100 in binary is expressed in octal as 4. And 000 in binary is the same single digit 0 in octal. If binary or octal conversions are new to you, take some time and get to know these. They can certainly provide value when you're converting these permissions. But know that if it's providing challenge or it is too new to you and you still wish to take time to learn this, you'll always be able to express your permissions using the symbolic representation we talked about previously. Bringing what we just saw back to our notes here, let's go ahead and talk through another way to consider this binary octal conversion. When we have our numerical values understood, this will be a powerful tool for you. Let's think about the digits that we have that comprise a set of permissions, R, W, and X. When using the numeric method, we'll need to represent each of these with a value in octal. In the 3-digit octal numeric representation for permissions, each of the digits we'll create stands for one access level: user, group, and other. In order to determine the digits, here's an easier explanation on how to do the math. Step 1 has us starting with 0. We'll then take the permissions for one of the groupings. In this case, we would start with user. If the user had the read permission, in other words, if read is enabled for the user, then we'll add 4. If the write permission is enabled, we'll add 2 more. And if the execute permission is enabled, we'll add 1. This gives you a total of 0 through 7 as options for the user access permissions. For example, if we were given this particular string of permissions, we can see that just the first 3, RWX, are available for the user. This means that a 4 for read, a 2 for write, and a 1 for execute would all be enabled and therefore all adding up to 7. Our octal representation for the user permissions is 7. The next digits that correspond to the group permissions are R-X. R-X would be a +4 for the read permission, +0 since we don't have the write permission, and +1 for the execute permission, or 5 in total. Our group permission octal value would be 5. Lastly, since other has 0 permissions, we don't have to add anything and the value would be 0. Putting these 3 numbers together, we realize that the permission structure RWX R-X -- corresponds to the octal value 750. Once we know how to calculate these, we can then use the chmod command to change the mode bits in this same fashion. Here you can see an example of using the change mode command along with the octal representation of the permissions we wish to set. Here you can see an example command using chmod to change the mode bits and an octal representation for the permissions they wish to set. RWX each corresponds to 4, 2, and 1. So we can determine that a 6 means that we wish to have the read and write bits for user. The 4 means that we have the write bits for the group user, for the group ownership and members. And the last 4 means that we have the write permission for all others. Another way to express this would be to say -RW, then we would not have the read permission, we would have the write permission, and we would not have execute. and the same would be true for other. In this next example, we see the user set up with 750. We saw this in our previous example exactly, but let's go ahead and write out what this would look like. If we had the user set up with 7 as its permission, that's all 3, read, write, and execute. A 5 is a 4 and a 1, so that is not read, but does have a write, worth 4, and an execute, worth 1. Lastly, a 0 means no permissions to other. With practice, you'll be able to do these octal conversions in your head, and it'll make more sense. If you find it easier, you can always rely on the symbolic representation using UGOA, the plus, minus, and equal sign, and then the permission letters R, W, and X. Now that we understand more about what permissions are set for the user that owns the file or directory, the group that owns that file or directory, and all others that wish to interact with it, now let's discuss how we change ownership. Perhaps we need to change which user owns the file or which group owns the file. In this case, we have other commands to do that. First, we'll take a look at the chown command. The chown command, short for change owner, is used in order to change the user that owns a file. This command can also be used to change group ownership, but we do have another command to do that as well, namely chgroup. If we were to want to change the ownership of the test file to the new user's student, we could use this chown statement. Chown, the new user that we wish to own the file, student, and then the name of the file, test file. If we had a directory, test directory, and wish to change the ownership for it as well as all files contained within, we can use a different option to the chown command. The -R option will allow us to recursively change ownership not only of the directory, but of all files contained within. We can see an example of what a command that does that looks like. Here, using the chown command with a -R and specifying the username student would change the ownership of the test directory declared by the argument as well as all files contained within. The chown command, as I mentioned, can also be used to change group ownership of files. When we wish to declare a group change as opposed to a user change, we need to declare it as a second field. To distinguish between the two fields of user and group, we separate them with a colon. In the first example, you can see changing only the group and not changing the user by using this technique. Here, we can see that the chown statement leaves no argument for the username to change, but the colon specifies that anything after the colon is a group we wish to use to change ownership for the directory testdir. After this command executes, the testdir, test directory, would then be owned by the group admins. If we wish to both change user and group, we can do those simultaneously. Here you can see an example of the syntax doing exactly that. The chown statement is coupled with both parts. The first part here shows the new user visitor. The second part here, separated by a colon, shows the new group ownership of guests. This allows us to change both the user and the group that own the test directory. And while chown can do both user and groups, it is important to know that we have another command that specifically only manages groups. The chgroup command, chgrp, is much like the chown command, change ownership. However, it only works on group names. That concludes this section. I look forward to seeing you in the next video. In this guided exercise, we'll take a look at managing file security from the command line. Let's go ahead and get logged into our instances and begin the steps. The first step asks us to become the root user. That should become quite routine for us at this point. Now we're asked to create the group A team. We'll then create 2 new users who are members of that group as a supplementary group. Alright, so let's do our group add. A team, then we're going to do a user add -G A team, and our usernames are Andy and Alice. Andy, Alice. Let's see, password. We see the users, tail etc group. Okay, and then we can do ID on Andy, ID on Alice. Everything looks like it's in place. Create a home directory in /home called ateam-text. Okay, easy enough. I'm not even going to change directories. I'm going to use an absolute path. So make dir /home/ateam-text. Yeah. ls/home. Got a lot of users hanging out in there and such, but we can see our new ateam-text folder there. Change the group ownership of the ateam text directory to ateam. So we'll use a chown statement. We don't want to change the user, then a colon, and then ateam on /home ateam-text. If we do an ls-al on home ateam-text, we can see that it is now owned by the group ateam, represented by the dot. We should be getting familiar with this dot and dot parent directory or the current directory. In this case, the current directory was specified in the argument for the output I wanted. Okay, now we want to ensure the permissions of ateam-text allows group members to create and delete files. So we want to give writable permissions to the group on the directory. So that's a chmod group adding write permissions for the home ateam-text. So if you do ls-al on home, we can see the ateam-text folder here. We can see that the group now has that write permission. Now we want to forbid others from accessing its files. So anyone that isn't in the user or group ownership category, we want to make sure they have 0 access. So currently, let's take a look one more time. We currently have 775, or fully read, write, and executable for user and group, and then read and execute for everyone else. Let's use the octal here, and we'll chmod 770, 0 permissions for other, on home ateam-text. Giving that a look again, we've now stripped away those permissions from the other set, these last 3 bits pertaining to the other category. Now we want to switch to the Andy user, so we'll exit out of root and then switch to Andy. Okay, who am I? I am now Andy. Navigate to the home ateam-text folder. It says remember to open a terminal window first. I'm there. So let's cd to home ateam-text. cd home ateam-text. Show you my current working directory. We'll touch a file called andyfile3. And we can see that file now exists. So great. It's set to record the default permissions here. So as we can see, that's a 664, it looks like. Yeah. Matches just fine. Change the group ownership of the new file to ateam and record the new ownership and permissions. So we'll do chown. Again, we're not changing user, so nothing there. Then a colon, and then the group we want is ateam. And then we want that on andyfile3. Do a little ll. And we can see that the group was now updated. Carrying on. We want to exit this login and switch to the user Alice. So I'm going to exit. I guess the word of caution here earlier to make sure you still have a terminal open is if you happen to exit too many times, your terminal window could close. So potentially even severing your connection to the server. So stay connected. We're just switching users here. So now I'm going to sudo su-alice. Do a who am I. Let's clear the screen a bit. Now we want to navigate back to this home ateam-text folder. So cd to home ateam-text. We can see the andyfile3 still sitting there. Determine Alice's privileges to access and or modify andyfile3. So let's try to echo text into there. Put some edit permission to the test. So if we say echo text out to andyfile. Now if we were to try to cat the file to see our changes, we could cat andyfile. And sure enough, we were able to edit it, no problem. If we didn't set our permissions correctly, it would result in a permission denied error. Luckily, we've been following along, and if you were as well, you should be able to edit and review that file. That is the read and write permissions for the group that Alice belongs to, namely that A-team group. If you were unable to access that file and edit the file and display its contents, it's likely a piece of the configuration that you missed. The setup here was a new directory owned by a group. We changed the group ownership there. And then we had that group was created and contained the 2 new users. So you needed to create the group, add the 2 users, adding them into that group, create the directory, have it owned by that group, and then adjust permissions to allow read and write permissions, or full permissions as the case were, to anyone within that group. So if you were able to follow along and do all that, you should be able to see this. If not, just backtrack and review a few steps and see what went wrong for you, and hopefully you'll be able to spot it and correct it. That concludes this guided exercise, and I'll see you in the next section. Special permissions exist within the file permission structure and constitute a 4th permission type. This goes beyond the basic user, group, and other types. These permissions provide additional access-related features over and above the read, write, and execute we've seen previously. Let's look at the special permissions that we have. In this table, we can see the effects of the special permissions available to us for files and directories. Our first special permission pertains to the user permissions. U plus S, or the set UID bit, allows files executed as the user that owns the file, not the user that ran the file. So any user who has permissions to execute a file, when the file executes, it will execute as the user that owns the file rather than the user that issued the command. This has no effect on directories. The second special permission, it pertains to groups. We call this the set GID bit, and it's expressed with G plus S. Much like the set UID bit, this means that file executions of this file will always be run as the group that owns the file, not the one that ran the file. Additionally, on directories, files newly created within the directory will have their group owner set to match the group owner of the directory, as opposed to the group ownership of the member who created the file. Our last special permission falls on the other category of permissions and is called the sticky bit. For an individual file, the sticky bit has no real effect. However, sticky bits being set on directories allow users with write access to the directory to only be allowed to remove files that they own. They won't be able to remove directories or files owned by other users. A good example of where this special permission for the sticky bit is employed is in the /tmp directory. All users have access to read, write, and execute from that directory. However, with the sticky bit set on that location, you may only remove the files you yourself own with your user. An example of the set UID bit is the command file for the password command. It's located in user bin password. You can see the output of an ls-l on the permissions of the user bin password command. These permissions include a set UID bit in place. You can see it denoted in the permissions with the lowercase s that we see here. This means that whenever we invoke the password command, it always runs as the user that owns the command. This is what allows any user the ability to set their command because the password command runs as the root user. An example where the set GID bit is used in our file system exists on the run log journal. You can see the output of an ls-ld on this directory. The directory run log journal has the set GID bit in place as shown here. This means that whenever we interact with the files in this directory, that the execution of those commands will run as the group systemd journal. Additionally, files created in this location will inherit the group ownership systemd journal, no matter who creates them. Lastly is an example of the sticky bit being set on the /temp directory. Here you can see the annotation of the T in this last field for the other permissions. This corresponds to the sticky bit being enabled and results in only being able to remove files that you personally own. In this case, only the root user would be able to remove this file. Recalling how we set permissions from our previous section, we can extend that information to include these new special permissions. Here you can see the symbolic method of using U plus S, G plus S, or O plus T in order to add these particular special permissions. When we use numerical representation, we have a fourth preceding digit that will set either the setUID, setGID, or sticky bits in place. Here you can see examples of setting the GID bit on a directory using the G plus S syntax, and then here you can see an example of setting the GID bit using the octal nomenclature. Notice that the octal nomenclature requires you to use an additional digit when setting the permissions. Here, the number 2 preceding the 770 permissions denotes the setting of the GID bit. When we wish to adapt these, we need to understand the pieces that come into play that set those initial permissions. The first of these is whether you're creating a regular file or a directory. The second thing that impacts these permissions is something called the current Umask. If you create a new directory, an operating system will start by assigning its octal permissions 0777, or full access to that directory. If you create a new regular file, the operating system designates the original octal permissions 0666, or full read and write permissions, but no execution. When it comes to files, you'll always need to explicitly set the execution bit, so we don't end up with rogue scripts or malware infecting our environment. Once the file has initialized with these default permissions, the Umask then comes into play. This is what we call a bit mask, and we'll use to overlay the permissions to adapt them to the proper initial permissions we wish to set in our environments. Consider the following output from the Umask command. Here, the execution of Umask shows 0002. This is an octal representation of the value of the current bit mask that will be applied. You can omit any leading zeros in the Umask before understanding what will be set. Default values for all Umasks in the bash shell are set in a few files, etc profile and etc bash rc. You can override these default values with your own local users' hidden files .bash profile and .bash rc. Let's look at an example of what the Umask does when creating new files and directories. Given this output, we can see the Umask is currently set to 0002, or 2. When we create a new file named default, we can view its initial permissions as read-write, read-write, and read. When we create a new directory named default, we can view its permissions as read, write, and execute for both user and group, and read and execute for other. When we adapt the Umask value from 0002 to simply 0, and then create files and directories, we should be able to understand the difference in the permissions that get created. Here, we'll touch a 0.txt file. We can then see that the resulting permissions allow us to have a write permission for other. This was not in place originally. Additionally, when we create a directory, we see that the permission includes full permissions for all user, group, and other. Initially, with a Umask of 2, we removed the write permission for other. Now, with the Umask set to 0, we allow the creation of all permissions when we create a directory. If we were to want to mask all the file and directory permissions for the other permissions, we could set the Umask value to 7. The value of the Umask is the removal of those bits no matter what is created on the initial file. When we set a Umask value to 007, we're denoting that the other bits should all be removed, read, write, and execute, and that no permission should be extended to others. Here we can see an example of that being used. The Umask is set to 007, and then, when a file is touched, we strip away all permissions for other. The same is true for directories. With a Umask of 7, all permissions are stripped away from the other access. A Umask of 027 would result in all permissions being stripped from other and the write permission being stripped from group. In the output below, after the Umask is set, you can see that the group permissions do not include write, and the other permissions have none. As the root user, you can update the Etsy profile.d local umask.sh. This will allow an adaptation of the default values that get supplied when you create new files and directories. It is in this fashion that you can adapt your operating system to properly put permissions in place when creating new files and folders that conform to the standards of access you wish in your environment. That concludes this section. Join me in the next video where we explore these new skills in a guided exercise. Welcome back to our guided exercise on controlling new file permissions and ownership. You should be able to experiment with Umask, default permissions, and the specific adjustments to these things throughout this guided exercise. Step 1 asks us to sudo and switch to the Alice user. If you don't have this user, it was created in a previous guided exercise. Feel free to either revisit that guided exercise or simply create the user now. I'm going to sudo su-alice. Who am I? Now we want to inspect the Umask that is set in this environment, by default anyway, for Alice. So we simply type Umask and we can see that it's 0002. We want to create a new directory, temp shared, and a new file within called defaults. So let's make the directory. We can take a look at the permissions, and then we can create the file and take a look at its permissions. So make dir temp shared, and then we can ll temp shared. Oh, sorry. Let me show you temp shared. Right, there we go. We can see we get a specific set of permissions that look like this. And then it was create defaults. So touch temp shared defaults. All right, and we can see what the default permissions are for that. So now that we've just created a directory and a file, we understand what default permissions are applied at that point in time. Now we want to change group ownership of temp shared to a team. Again, this is a group created in a previous exercise. If you didn't perform that guided exercise, feel free to go back in the chapter or just simply add that group now if you're familiar. So we'll chown, no user change, just a group. And we want that on the folder temp shared, so we can do ls-al temp shared and see that we are now owned by the a team group. Now we want to create a file in temp shared and record the ownership and permissions. So we'll create, it looks like they want us to create Alice3, so we'll do that. So let's touch temp shared Alice3 and then do an ls-al on temp shared Alice3. Looks like we're getting 664 as the default permissions with an Alice ownership. Now that we are asked to do the same again for Alice4. So let's just do that real quick. I can just up arrow, get a 4, up arrow, get a 4, and I can see that that gets the same. So if I just do ls-al on temp shared, I should see those files side by side. Great. Looks like everything's working as expected, just the default Umask being applied. Now we want to change the Umask for Alice such that new files are created with read-only access for change the Umask for Alice such that new files are created with read-only access for the group and no access for other users. Then we'll create a file and record the ownership there to see that new Umask being applied and stripping away. Then we'll create a file and record the ownership there to see that new Umask being applied and stripping away that permission. So the Umask we're looking for here is 027 to remove bit 2 and bit 7. Bit 2 from group and bit 7 from all 7 bits from other. Group 2 corresponds to that write permission. So we want to make sure to remove write permission for group, the middle digit, and we want to remove all access from the other bit, the 7. So we're going to do a Umask 027. All right, and then we can just do a simple Umask to see what it's set to, verify our work. Now we want to touch temp shared Alice5. And then we can just up arrow to get our ls command, and we can see, look, now we've removed bit 2 as well as all 7 bits here, which was only applying the read, but make sure all 7 bits are removed. So umask 027 is going to make sure group does not have write and other has no permissions. Log out and log back in as Alice, starting a new shell, and then view her umask. So let's start by seeing umask, right? And then we're going to log out, and then we should be able to just log back in and then do a umask. Oh, look, it didn't stick. So important to note that it reverted to her default setting. So if we want to change this permanently, we'll need to change the default umask for Alice to prohibit all access to other on files the user creates. So then we want to append the umask to 007 at the end of Alice's .bash rc file. These are the local customizations that Alice will be making to her own bash interactions. So if we add this value into the .bash rc, a hidden file in the home directory of the user, then this will be applied every time the user launches a shell. So let's go ahead and echo umask 007 out to her bash rc, and then we can see that. Alternatively, if you didn't want to use echo, you can edit this file, perfectly acceptable, however you wish to go with it, but I'll just go ahead and use the provided example. Echo umask 007, quote. Now, very important that you're using 2 output redirections. One would completely overwrite the file and you'd lose everything contained within. So make sure you're familiar with that concept. Okay, and then we'll do that, and we'll cat the home directory of .bash rc for Alice, and we can see that specific user aliases and functions area at the bottom of the file. We've customized and added this umask. All right, let me clear the screen. Now we want to log out, log back in as Alice again. So let's just show the umask. It's showing as default. I'll just do the umask. I'm going to set it to something else. Let's say 027 like we did in our other earlier part of the exercise. Now I'm going to log out just so we can see we manipulated it, and we can log back in as Alice. And what would you think it should be? Right? We added to the bash rc file the 007 umask. Let's see what gets applied when Alice logs in this time. There it is. So that .bash rc file takes in those customizations we wish to make to the bash environment for Alice, and you can see we've now added an entry that customizes Alice's umask to the 0007 or 007, ignoring that initial bit if you want. In this way, you can customize how files behave upon new creation and manipulate the environment to make sure that the proper permissions are applied for new files when you create them as your user. Remember, we'll simply supply that argument in the user's custom area of the .bash rc file located in their home directory. That concludes this guided exercise. I look forward to seeing you in the next video. Welcome back to the lab. Let's go ahead and go through this solution to make sure we all have the opportunity to see how this works. I'm already connected to my environment, so let me go ahead and switch to the root user. All right, so I'll just do a simple sudo su dash, and who am I, just to show you I am indeed the root user. Okay, so we'll create a new group named operators. Group add operators. And we can see that it was then added to the tail end of our etc group file. Now we're going to create 3 users and add them to the group operators, making it a supplementary group. In my case, I'm not going to set a password. I'll just leave these accounts locked. I have enough user accounts floating out there that unless we explicitly need to leverage these users, I'm just going to leave them semi-disabled. Creating Yasmin, Luis, and Liza. So we're going to do user add. Remember, we use this capital G for secondary groups. We're adding them to the operators group. And it was Yasmin, Luis, and Liza. Okay, and so we can do an ID on Yasmin, ID on Luis, and an ID on Liza. And we can see that they all 3 have these supplementary group operators. Now we're going to create the home operators directory. It's a simple makedir command. Okay, and we can ls home to see that directory and a bunch of other user directories here. Now we want to change group permissions on the home operators directory so that it belongs to the operators group. Okay, so let's first look at home operators to see what it is by default. Okay, currently owned by root. So we want to chown the group to operators for home operators. And then I can run this command again to see that change. Perfect. Set permissions so that we have the GID in place, that owner and group have full permissions, and other has none. So the GID bit is the permission 2 out of our special permissions. So that first bit is 2. Since we need full read, write, and execute for user, that's 7. Same for group, 7. And since we want no access for others, that's 0. So we'll chmod to 770 home operators. Okay, and then let's take a look at that. Now you can see we do have 7 for the user, 7 for the group. Since this is a lowercase s, we know that you do have the permission. Since it is an S, we know you have set GID, since it's the group bits, right? We have the special bit indicated, so that means it's enabled, and since it's lowercase, it means you do have the permission here. If we did not have the execute permission, this would be a capital letter. Now, we want to check our work by creating some files, touching a few files here and there, switching users and testing access, and then that should complete our work. So, or at least our verification. I believe our work is actually done, but let's go ahead and log out of root, and we'll sudo su-yasmin, right? And then we want to cd over to home operators, and let's see, we'll just touch something, right? Touch yas.text. All right, great. So that was certainly possible. So let's log out of this user. Now, just as my default EC2 user, let's see if we can cd over to home operators, because we're not in this group. Oh, nope, denied. So that's good. And then, do we need to test any other users? Oh, let's test one more. Let's try Lewis, I guess. So let's sudo su-lewis just to verify our work. And let's touch home operators lu.text. That worked. So we know that Lewis has the permissions he needs, and the files exist. So it looks like, and we could assume the same for Liza, created the same way. So our new users have the access they need, full access into the group-owned new directory, whereas our default user, our EC2 user, does not have access, not in the group, right? Well, that concludes this lab and chapter. I hope you were able to follow along and accomplish these tasks. If you'd like to review some of this material, just go back in the chapter and even reattempt some of those guided exercises if you need to hone those skills. That environment. Processes are nothing more than a running instance of a launched application. Whenever we execute any program, a set of one or more processes is then launched and managed throughout the operating system. Processes consist of several parts. First is an address space of allocated memory. This is something that the operating system kernel will manage, but it is something you need to be aware of is occurring. Secondly, a set of security properties are applied to a process. This relates to the ownership credentials and privileges for that specific executing program. Next, one or more execution threads of program code are launched into action. This is the intended actions when you launch a process, namely opening a piece of software, executing a set of instructions, or running through the steps of an authored script. The next thing we need to know is that each process is managed through a number of process states, and we'll look at what those states are in this section. Processes all run within their own unique environment. The environment of a process is what defines several aspects of its execution. This will include any local or global variables that are invoked throughout the running of this process. There'll be a determined current scheduling context for the process. And lastly, the allocation of system resources as managed through the system kernel will need to be appropriated. This includes things like network ports if it's communicating over the wire, or file descriptors as it creates and manages updates to and from files. We have a concept of multiple tiers of processes. The initial instance of a process will become known as the parent process. Parent processes often duplicate themselves into child processes. This duplication is known as a fork, which allows a process to duplicate its own address space and run additional processes of the same type. Each process is identified with what is known as the PID, or Process Identification Number. The PID for each process should be unique and allows for tracking of these processes throughout their execution. When a process spawns child processes, this child process will also keep track of the parental process's process ID. We'll call this parental process ID the PPID. So in this way, a child process will have its own process identification number, but will also keep track of the parental process identification number of the process that spawned it. Here we can see that a process is created. Starting at the left, that process may proceed forward and create child processes. At this point in time, the child process is running or executing, and we see the exec statement in this case. From there, a child process can either conclude or spawn its own child processes as pertinent to the particular application and execution. Once the work of a child process concludes, it will return control to its parental process for it to resume to its conclusion. From there, the parental process will finish its work and conclude in much the same fashion. We do have several instances where a child process, or any process really, may lose track or fault in some way and can result in what is known as a zombie process. This is an unintended, orphaned process that is hard to control and is an unintended result within our operating system. Know that these exist, and we may be able to look at these throughout the rest of the sections. Processes, from their inception to conclusion, go through a number of states as they run in the operating system. Since our operating system is multitasking and managing a number of processes simultaneously, it has an elegant way of setting process states in order to determine which processes should run, in which order, and how to manage the allocation of resources from the system to allow this to occur gracefully. Here we can see a diagram that has a number of these process states defined. Let's take a look at this diagram so we can understand the states that many processes can find themselves in. From the left, we're seeing a new process get forked or created. Once created, it will be scheduled by the system. If it's ready to be executed, it can be set into a runnable state. This means it is capable to be executed, but may or may not be executing at this current time. From that state, we can either stop or resume the execution of that process, and a state of stopped would be applied. Many mitigating factors can determine whether or not we change a process state, but in the general flow of a process, we would go from runnable to running and then conclude. Several other states that happen within, in order to manage the processes and resource allocations for the system, are to stop or sleep this process. Sleeping allows a process to wait until a later point in time before resuming. It may be necessary to put the process into a sleeping state while other work concludes that are dependent on the execution of this process to resume. Once a process is completed, we'll reap those resources and return them back to the kernel for other process executions. And at that point, the process will exit. If something is lost along the way, we can end up in the resulting state of a zombie process. This is not ideal, but is something that we can manage in our operating system, or at least understand what happens when zombie processes occur. Should we have a zombie process, the operating system may have the inability to reap back the resources that were assigned to that process. Zombie processes stacking up in this order can render a system unable to process further requests because all allocated resources are locked into these unmanaged and now zombied processes. This is uncommon to occur and typically occurs only in poorly authored code or poorly administrated systems. Now that we know what processes are, let's take a look at how to list processes running within our operating system. Before looking at the listing of processes, it's important to understand why we care about process states. When you're in the process of troubleshooting any system issues, you'll need to look at where system resources have been allocated. The kernel continually communicates with ourselves as we probe and with running processes as they execute in order to manage the resources of the system itself. When we take a look at running processes, we have a number of commands to do so, and caring about the states of these processes means that we'll have relevant information available to us through the output of these commands. The first command to look at is the top command. The top command gives us a list of running processes consuming the most resources at the given moment in time. The S column in the output of the command top as well as the stat column in the output of the command ps, both of which we'll explore momentarily, gives us information about the state of these running processes. When we see processes listed out in this fashion, we oftentimes see a number of them in the state lettered R. This means that they're runnable, but may or may not actually be running. As things progress from start to finish in the form of processes, we can monitor them throughout their life cycle to see a successful conclusion. Here we can see the output of two specific commands, top and ps. Here, taking a look at the top command, we can see an example of the state column. The state column is shown here and represented by the letter S. In the output of the ps command, we can see a similar set of information in the stat column. The stat column here corresponds to that same status or state. Now that we understand what processes are, let's take a look at listing processes. When it comes to inspecting the running processes on our system, a main command that we'll go to oftentimes is the ps command. This provides us detailed information about processes executing within our system. When looking at the output of the ps command, you'll need to learn a few specific bits of information that it's supplying to you about the processes. First, we'll learn the user identification information about the running process. This is the user that the process is running as, and will determine things like privileges and security implications throughout the execution of the process. Next, as we discussed earlier, there is a unique process identification number for each process known as the PID or PID. If this is a child process, there'll be the companion parental process identification number tracked as well. The ps command will also keep us informed of running real time of CPU usage for the process in question. Additionally, we'll learn about how much memory the process has been allocated in its various locations throughout the operating system. If this process writes out to some component or file, we'll learn the location of the process's standard output. This is also referred to as the controlling terminal. And lastly, a critical piece of information is the particular state that the process is currently in. We learned briefly about these process states, and we'll look at more of this as we inspect individual processes. As we've started to grow our repertoire of commands, we've started to use command options or flags. When it comes to the ps command, we can use any of three specific formats that are available for many commands within Linux. The first command is the one that we've seen most regularly, which is known as the Unix or POSIX options. These can be grouped together and are preceded by a single dash. We've seen this as we've used the copy command and the ls commands in previous sections and chapters. BSD options are available as well, and the way to express those is that they may be grouped together but do not require a dash. We've not yet seen a command that we've used this interpretation, but we've seen something similar. In the BSD expression, we no longer require the dash to begin our flags for the options we wish to invoke. And lastly, while we've discussed it, there's also the GNU long options. These are preceded by two dashes and typically invoke the entire word or phrase to describe what the option does. Here you can see ps-aux, which is an expression in Unix or POSIX terminology, is not the same as ps-aux. For this command, we will have the same outcomes from these particular flags, but the expression here is one that's differing between the Unix or POSIX nomenclature versus the BSD style of expressing options. I just wanted to call that out simply here because PS is one command that takes all three styles of these options. I'll use these interchangeably throughout the rest of the course, depending on the particular command or circumstance, and I want you to feel comfortable understanding the differences between these types of expressions. When it comes to the PS command, the most common set of options administrators use is the A, U, and X. This isn't short for anything like auxiliary, but this is three specific options for the PS command. Let's go ahead and jump in our terminal and take a look at what ps-aux provides as far as information. From our terminal, let's go ahead and run the command ps-aux. This provides us output about a number of running system processes. Highlighting one single line, we can see all the information provided. If I scroll up to the top of this output, I'll be able to see the column headers to describe what each of these bits of information are. Let me scroll up now to show that. Here we can see the column headers. With my font this large that assists us in being able to capture the output for these recordings, I have a line wrap. Let me reduce that now simply so we can see this information on a single line. We can see that it's providing information about the user that this process is running under, the PID of the specific process, the resources that are being allocated for this process, and a number of other bits of information. The one that we discussed previously on state is shown here. Lastly, some additional information about when the process was initiated, as well as how much time it's been allocated for CPU resources, are provided. The last field tells us the command itself that's being executed, and you can see an example of that in the first entry here. The command also includes all of the various options that we're running for that process. We can see as we continue to flux between the various options for the PS command, we can get different information out of the command output. In the output included here, we can see the output differences between the PSAUX command, the PSLAX command, and the PSEF command. Depending on your needs as you inspect processes, you can combine and use the various flags available to the PS command to get the relevant information for your troubleshooting needs. By default, the PS command gives you all processes for the current user. This correlates to all the processes running in the given terminal the user is currently using. When we see processes in brackets, that means that these are scheduled kernel threads. When we see the dreaded zombie processes, these are typically listed as exiting and no longer actually updating that status and closing out, or defunct. The process itself will try to continue to exit for only so long before declaring itself defunct. The output of a PS command will only display the values once for the current moment in time that the PS command was executed. If we wish to see a running monitor of these processes, we can utilize the top command. The top command by default will update every several seconds in order to refresh the information about the running processes. The default output is initially sorted by process ID for the PS command, while the output for top will always be sorted by the top consumers of the particular column that you're sorting the output by. This sorted output can be adjusted as you're reviewing the top output, and for PS we can pass in additional flags or options to determine the sort order of the PS output. That concludes this section on processes. I look forward to seeing you in the next video. Now that we're familiar with what a process is, we'll need to learn how to inspect them and describe jobs as well as their sessions. From there, we'll proceed in how to interact and control these various jobs. Job control is a feature exposed via the shell which allows a single shell instance to run and manage the processes within. A job corresponds to each interaction via the shell prompt. While many of these jobs execute quickly, we can interact with the shell and launch sophisticated applications or even long-running scripts. Once we hit enter from a bash interaction from the shell prompt, the pipeline of processes that gets created are all tracked and categorized together. We refer to this group of processes as a process group. Even some of the simplest single commands can launch a myriad of processes that are collected into a group in order to track the execution from start to finish. When we do so from the command line, we typically expect to enter a command, press enter, and have the results return and return us to our prompt. In this way, we're executing jobs or processes in the foreground, meaning we're watching and waiting for their results. The foreground processes are ones that control our terminal. In this way, when we hit enter on a command, we have to wait for the job to conclude before we're returned back to the prompt and allowed to issue further commands. This is only one way that we can interact with the commands. Oftentimes we wish to launch long-running processes or really explicit commands that have a lot of work to do, and we may not want to wait for that work to conclude. In this way, we can run what are known as background processes. Being able to launch a job and place it in the background allows us to continue our work on the command line without waiting on the resultant conclusion of that process. Once we've pushed that program into the background, it's also important to know how to recall that information to the foreground when we're ready to work with it again. We also need to understand that as we run it within a terminal, each terminal is known as having its own session. A session can be comprised of both the foreground processes we're interacting with from the command line directly, as well as those that are running independently in the background. This collection of processes together is known as our session. All jobs, whether in the foreground or background, do belong to one specific session, and that information is tracked in the value known as the TTY. When we look at the output of the PS command, we're provided with information about which TTY a specific process is attached to. This lets us know which session the process is running within, and we can find like-minded processes running from the same session through various sorting methods. When we have system processes, also known as system daemons, that are not necessarily associated with a single TTY or session, the output of commands like PS will note this field with a question mark. When you see a question mark in this output, just know that the TTY is something more universal to all users of the system as opposed to locked to a specific session for a given user interaction. This makes sense when we consider that system daemons and system-wide processes are consumed by all users no matter which terminal they're logged in with. Now that we understand process environments, let's take a look at running jobs in the background. As we mentioned, we've seen ourselves run commands in the foreground, namely, type a command, hit enter, and wait for the resultant information to be supplied, as well as a return to the shell prompt. We discussed in the last section that we can do this same type of work and place these jobs in the background. If we wish to launch a job in the background, we need only do so by placing an ampersand or the and symbol at the tail end of the argument itself. Have a look at the command shown here. In this output, we're taking a look at a sleep command argument. Sleep allows the operating system to wait a specified number of seconds. In this case, we're issuing the command for the operating system to sleep for 10,000 seconds. We may not want to sit and watch that to occur, so we'd like to do that in the background. In order to run this job in the background, we simply add the ampersand to the tail end of that argument, and it will be placed into the background. When we do this, we're also told the PID or process identification number that is created for this job. We're immediately returned to our prompt and can continue our work while that job executes in the background. Now that we know how to launch jobs into the background directly, you'll need to know how to view the jobs running within the background. For this purpose, we have the command jobs. Here you can see an example of running the jobs command with the previous sleep command running in the background. If we were to have multiple jobs running in the background, they would all be listed here in the output. If we wish to bring that command back to the foreground and wait for its output to conclude, we can do so with the command FG. The FG command takes an argument of the job ID number. We'll specify it with a %, and it corresponds to the output of the job's argument. If we look above, we can see that the sleep arguments are corresponding to the job number 1. If we wanted to bring this to the foreground, we'd use the FG command with the %1 in order to bring the sleep command back to the foreground. Here, we would now wait at the command line for this job to conclude before returning us to a prompt. If we wish to then proceed to put this back in the background, instead of waiting for it to conclude, we have a simple shortcut to do so. To send any foreground process to the background within our terminal, we'll need to use the Control-Z command to do so. Once we press Control-Z, the command is placed in the background but is suspended from execution. We can see the output here that shows the status stopped and the arguments for the command sleep 10,000. For the PS command, we also have the J option. This will display information relating to jobs. With the output of PSJ, we get some other specific information bits about jobs running in the background. We'll be given information we've seen before, namely the parent process ID and process ID of the process we've got running in the background. However, we'll be given some additional information. We'll get the process group identification number, as well as the session ID for the terminal that has launched the job. These bits of information allow us to correlate the running process or slept process in the background to the session and process group it originated from. With the example we're using, the sleep command is currently suspended, giving it a process state of the letter T. Here is the job we placed in the background. And we can see that the argument for its state is indeed set to T. While this process is in the background, if we wanted to start it from a suspended state and into a running state, we can use the BG command to manipulate the jobs in our background. Here, if we wish to resume the work that the sleep command was doing, we could use a BG argument that corresponded to the job number, %1, in order to resume the work of the sleep command we have in the background. If you were to try to exit your terminal and still had jobs running in the background, a terminal warning would be displayed that lets you know that you still have these jobs that if you'd like to manage them, running within your background. If you proceed to exiting your terminal, these jobs would be terminated. That concludes our section on running jobs in the background. In our next section, we'll take a look at a guided exercise where we can use these skills in order to manage background and foreground processes. Welcome to our guided exercise on background and foreground processes. Just in my home directory, I'm going to make dir bin, I'm going to cd into bin, and then vim forever. Now we just need to type this out. So first #bang, and then we always start these files with the interpreter. So here, you don't have to worry too much about what all this means. Just a simple script. We'll start with, we're just saying that this is a bash script. Then while true, do. What are we going to do? We're going to echo -n quoted $@quote, and then we want to redirect that output to append to some out file. Okay. Then we're going to sleep 1, so the output will get added to a file. Then we'll sleep for a second, meaning just wait and do nothing for a second, and then we're done. So simple little always writing to a file. So this will just write to a file once we execute the script, and it'll write to that file once a second until we stop the script from running. Okay, just take a quick look at the forever script. Looks good. All right, the next thing we'll need to do is make that executable. So chmod +x, the forever script. And if we do an ls-al forever, we can see now we have both a green color coding that wouldn't have been there and an X across all 3 places, user group and other. Now we're going to open that second window now and start forever running and appending to the out file the word rock. So I've now got a second terminal here. I'll leave this one smaller and just down here so we can sort of see what's going on there. I hope this isn't confusing for your view. And all we're going to do here is do a forever rock. Okay. So now let's go back to our instructions. Now in the other window, we're going to use a tail command to confirm that it's writing out to this out file. Okay, so let's just do tail. Let me go up a directory. I can see the out file was created, so tail out file. And it does, and if I were to do a tail-f, I'd follow the out file to see that it is continually writing this. Write it, sleep a second, write it, sleep a second, as we expected. Now let's, where we put the job running, whichever window you did that in, we're going to suspend the running process with Control-Z. We'll get the job ID returned to us, and then we can confirm in the other window that it no longer is outputting that the word rock to the out file. So here we are, rocking. Here I am. I'm going to do Control-Z. Stopped, and if I click back over here, rock is no longer being appended to the out file. Okay. All right, now back in the window where we're running the script, we'll view the output of jobs. And the key thing to take away here is that a plus denotes the current job. And if we want to restart it in the background, we can do so. So let's go ahead and run jobs. You can see the plus. And if we say BG, right? And then if we do jobs again, it is now running, which means that we can see in the other window, rock is starting to append to that file. I don't even need to switch windows. It's just sitting back there appending somewhere into that file. Now we want to start a few more processes which append strings to the out file. We'll use the ampersand so that these just immediately start in the background. And then we'll use the arguments paper and scissors in place of rock so we can tell all three apart. We'll do forever paper and an ampersand so it just immediately goes to the background, and forever scissors and stick that in the background. Now if we watch our output, I'm not switching screens, just being lazy here, we can see rock, paper, scissors, rock, paper, scissors, rock, paper, scissors. And if we say jobs, we should see all three of them running, rock, paper, and scissors. All right, now we want to suspend the rock process. So we'll use jobs to determine its job number, and then use Control Z on that. So we say, it's getting interesting to see with that background bit over there. So jobs, and then if we want to do Control Z, and do jobs. Oh, I forgot to foreground anything here. So let's, jobs shows that rock is task 1. So we're going to foreground %1, right? And then we can do Control Z. And then if we do jobs, it's stopped at the moment. And if you can see in my background, it's just continually writing scissors and paper, scissors and paper. Okay, so we were able to knock that one out. Now we want to terminate the paper process. So we need to foreground the job, then terminate it with Control C. So let's just run job. Let me clean this up. We'll do a jobs again. And so we want to foreground %, and we're terminating paper. So that's 2. Then we do a Control C on that. All right. And then if we look at our jobs, we only have the 2 left. And if we wait for that next line to wrap around, scissors, 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 scissors is going on. Okay, perfect. All right, so now we want to view the remaining processes, the remaining jobs, I should say, with the PSJ command. The suspended job has state T. The other background job is sleeping in an S. And since PS is on CPU, R while displaying. So PSJ T. So let me see. PSJ T. You can see the T here for rock. S for scissors, as we expect. Right, that's great. And then the R for the process, the PS command itself. Now we want to terminate the rest of the jobs. Terminate it using Control C for both rock and scissors. And then, it is nice to note that the job, when we bring it to the foreground, the one that stopped, the rock job, when we bring it to the foreground, it tells the job to start again. So temporarily, we should see rock being appended to our out file before we terminate the process. So let's just see if we can get that. Okay, so we have jobs, right? And then we want to foreground %1. Now let's just watch for that next line. We can see rock is now being entered over there. And then we want to just kill that one, right? And then if we say jobs, we only have scissors left. We see that going. We can just foreground. I didn't have to pass an argument. I could have passed %3, but we only have the one job, so it's smart enough. So I can hit Control C and notice that the file no longer is being appended to in the background there, or in the other terminal. I shouldn't use the word background. Then we're asked to just clean up a bit of work, so we Control C to end that tail. If we were to cat the out file, it's just a mess of the work we had there. So we just want to remove that out file, clean up our work a bit. And that concludes the guided exercise. Hopefully you were able to follow along with that and move processes to and from the foreground and background and control their execution. I look forward to seeing you in the next video, and I'll see you there. In this section, we'll take a look at how we kill processes. We'll look at the different characteristics of daemons, and then we'll end user sessions and processes using our new skills. Signals are used to interrupt running software. Each signal value pertains to a specific action you want to perform on the process itself. We'll take a look at this table so that we can understand what the corresponding results of the various signals are. Let's go through this table on the fundamental process management signals. When we pass signals, we do so numerically typically, but can also do so using a short name. It's important to be able to correspond both the numerical value and short name to the intended outcome by passing that signal. Our first signal, signal 1, is known as HUP and stands for hang up. This is a legacy term from the days of modem-based interactions, but pertains to when we want to terminate the process that's running. First signal, signal 1, is known as HUP and stands for hang up. This is a legacy term from the days of modem-based interactions, but pertains to when we want to terminate the process that's running. Signal number 2 is an interrupt signal. This will also cause process or program termination. We perform this work routinely on the command line with the Control-C command in order to break a command that's currently executing and return to our command prompt. The signal 3 is used for the quit signal. This will allow a process to gracefully exit and dump out the remaining information during its termination. This differentiates itself from being able to hard break or immediately end a process and does not allow the cleanup of its files and write out of a dump. Here, when we want that more elegant exit, we can use the quit signal. When managing processes, especially zombie or rogue processes, the signal 9 for kill is often necessary. This is a very aggressive signal and forces an immediate program termination. This can't be blocked or ignored and is always a fatal result. While this will become something you use routinely as a system administrator mitigating errors within an environment, it's something not to be taken lightly. You should always try to appropriately handle and exit gracefully processes when trying to troubleshoot. This is somewhat a weapon of last resort. Signal 15, or the terminate signal, is also available. This one is similar, but can be blocked, ignored, or handled more gracefully. This is something akin to a polite way to tell a program to terminate and allows for a self-cleanup of that exit. Signal 18, or CONT, is short for continue. If a process is in a stopped or sleeping state, this is the signal that will tell it to resume execution. Signal 19 is the stop signal. This will suspend the process. This can't be blocked or handled and is something similar to what we saw in our jobs handling section, where we place systems into a suspended state when they're in the background. Signal 20, or the TSTP shortcode, is a keyboard stop. This is like the previous signal, but in this case, it can be blocked, ignored, or handled. We've seen this with the Control-Z argument we've used when handling jobs. As we become familiar with these signals, we understand that they each have a default action. The term signal will cause a program to terminate or exit immediately. The stop can cause a program to stop executing or suspend its work until later resumed. Understanding the appropriate usage and differences between these signals will be necessary as you work to manage and properly administrate your environments. We've seen a few of these signals even if they were behind the scenes working when we use commands like Control-Z or Control-C. These are certainly shortcuts to providing these signals, but we have commands that allow us to more directly send the signals. The main command people use when wanting to issue a signal is the kill command. As it's typically used when troubleshooting rogue or errant processes, the command is named kill, but can be used to provide any signal that we've learned about. When we want to see a list of the catalog of signals we can send with the kill command, we can use the -L flag to list these out. Here you can see the output of the kill-L argument to list out all the various signals that can be sent using the kill command. These correspond to both their number as well as their shortcode to be able to be sent as arguments to the kill command. Here you can see an example of the kill command being used to send the sigterm signal to a process that has the PID or process identification number of 5205. After sending this, you can see the job is terminated. While the kill command works on processes individually, we also have the concept of a command that can work on multiple processes. Instead of using process identification numbers as the kill command did, we have the command killall, which can take the name of commands. In this way, we can use the killall command in order to signal a change of behavior for multiple processes based on that command name. In the output of the PS command here, we're looking for all jobs that contain the word job. We can see that we have several that contain the command control. If you were previously performing the work in our guided exercise, you'll be familiar with this concept. All three jobs have a different argument. In this one, we're running job 1 versus job 2, and in the last one, job 3. Because these have a similar named command, we can use the kill all argument on the command control in order to manipulate all of these processes simultaneously. In this way, we can see that all three of those jobs were terminated with a single kill all command. Another way we can manage our process signaling is using the pkill command. This will send a signal to one or more processes which match the various selection criteria. The pkill command includes several advanced selection criteria. Namely, we can search by the command name, the user who's executing the job, or the user under which the job executes, the GID, or the group that is executing, or the group under which the job executes, the parent process, or the terminal that it's coming from. In this way, we can search for and find the particular jobs we wish to manage and issue pkill statements to manage them all as a group. In the output here, you can see an example of the pkill approach. In the first section, we're using a ps command and a search via grep for pkill statements. And we can see 3 exist. We then can run a command like pkill control and terminate several of these at once. When we look back using the same command, we can see that we have a terminated control pkill 3. Lastly, we can search for a test argument and see that we still have a command test that's running from control. Another example is shown where we search for processes by username. In this output, all processes running under the username user will be displayed. Here you can see an example of a process running under the username user. In this way, we can issue the various signals to the processes that we filtered out using kill, kill all, and pkill, depending on what's appropriate for our needs. That concludes this section, and in the next section, we'll take a look at logging users out administratively. In this section, we'll look at logging users out administratively. When working in an environment, it's not uncommon to need to manage other users on the system. For any number of reasons, it may be required that you suspend or terminate their interactions with the system. In this way, we can use several tools in order to find who's on the system and manage their connections. As a former system administrator, the first command I would always run when interacting with any number of systems was always the W command. The W command provides a first look at some initial statistics about the environment, but one of the key things to note out of its output is whether or not other sessions are connected to the system. Have a look at this output of the W command. Here, we can see a bunch of useful system information. How long the system's been up and running, various load average information about the performance of the system, and mainly what we want to look at here is whether or not other users are connected. Each user has their own specific TTY or terminal connection. We can see how many exist, find our own, and determine if others are connected to this system. When appropriate, we may need to disconnect those other users to correct the particular system tasks that are errant or cause for troubleshooting. You can also see what those various users are using, whether they have their own bash terminal shell, or in the case of my own user here, what command is being run, such as the W command. You can take a look at other information from the other columns to understand when this user was logged in, if they've been idle, and how much time they're using on the CPU currently. Based on this information, you can make determinations about whether or not the user is active and whether or not you should terminate their connections in order to proceed with your own work. Depending on how we wish to manage the connection states, we can use a number of the tools we've recently discovered to either use a pkill command and potentially terminate all processes, or find one errant process or connection and terminate only the individual one using a kill type command. I do agree with this callout box, which says that the sigkill or level 9 signal is often used too quickly to aggressively tear down a process. It should also be considered that other signals exist to more gracefully end these processes. When troubleshooting, you'd like to end a process as gracefully as possible, because this can result in additional information being written out as the process closes out that can aid in your troubleshooting. Core dumps can be some of the most useful information when a process tears down if it's able to provide you with additional information in any of your analytic investigations through troubleshooting. Be sure to consider all the signals available to you when you're trying to manipulate a process and not always go to the signal kill for an aggressive teardown for anything that's errant within your system. Okay, looking back at connections we may need to sever for various users, we can consider a situation where we have a user Bob that may be connected and we wish to inspect their connection and make a determination, if not terminate, that connection that Bob holds open. When we use a command like pgrep, we can take a look at and search through the processes for any number of various things. One of the flags for the pgrep command allows us to provide a username and search through processes that are owned by that user. We use the pgrep command in collaboration with the option to supply a username from -u. We see all of the various processes that are running as the Bob user. We get their corresponding process identification numbers alongside them. We can then use a pkill argument and pass the signal we wish to use for any process owned by the user Bob. This would kill all processes run as that user, namely the entire list of the 4 we saw above. Once we run that argument and research for all processes running as the user Bob, we see that none exist in the system. While we used a very aggressive sigkill signal in the previous example, it's not always appropriate. Here we can take a look at a similar style interaction that uses a more graceful approach. Here the pgrep looks for all of Bob's processes, but instead of using a sigkill, uses a more graceful approach. This approach, pkill-t on the TTY3, only kills the processes running within the terminal that Bob is using to connect, but doesn't necessarily kill everything Bob is doing. In this case, the connection, or TTY, itself is not torn down. Bob will remain connected to the environment, but the processes running as Bob's user will be terminated. If we were to want to then further disconnect Bob from the system, we could proceed with a sigkill for the TTY3 connection that Bob is using. If we were to do that and then search for Bob's processes, we'd then see all processes and the TTY connection have been terminated. When trying to decipher what processes are connected to others, as well as to specific users that may have executed them, the PS tree output can be helpful in organizing the output. Have a look at this output of the PS tree search that searches for all of Bob's processes. We can see the relationship between the parent process of the bash connection Bob has initiated and the 3 processes that Bob has executed from within that bash shell. If we were to run a pkill argument on the process ID 8391, then we would specifically target the bash connection. Any processes running within that terminal would subsequently be torn down, as well as their children of this bash connection. If we were to issue the sigkill, we could then see that Bob no longer has anything except this connection. This is because we provided the -P 8391 argument that preserved the bash connection. This is another way to tear down the processes while not necessarily severing the communication connection that Bob had in place. That concludes our section on killing processes. I'll see you in the next video where we go through a guided exercise together to use these skills. Welcome to our guided exercise on killing processes. We previously wrote our forever script and we'll reuse that here. Step 1 asks us to start 3 processes from this script that append to the out file. We'll name one game, another set, and the final one match. We're asked to start all of these in the background, if you can see in the instruction examples, the command examples. All right, so I am logged in. So I'll say forever game, forever set, and forever match. And when I do an output of jobs, I can see all 3 are running. And let me go ahead and start my new terminal. New window. Let's do a tail-f out file. Game, set, match. Game, set, match. Game, set, match. Got it. Okay. We want to suspend the game process. So we'll need to foreground it, or we can simply apply signals to those running in the background. We'll use the same numerals that we'd use from the jobs output. So here we want to send a kill signal for the sig stop to the game process. In this case, mine does correspond to process 1 as well. So we'll say kill sig stop %1. Now if we just look over here, we can see that we're just getting match and set appending to the out file. Now we want to terminate the set process. We want to use the sig term signal. So we'll do a kill sig term %2, provided your second job is also set. So I'll just clean this up and I'll say jobs again. My game process is stopped. Set is my second process, so I'll do a kill. And we're doing a sig term. We're terminating. And here it's %2. Now let's take a look at this, and we just have match, match, match. Perfect. So only the third job is appending to the out file currently. All right, and let's take a look at jobs. And we can see the second job is terminated. All right, now we want to continue the game process. So we want to pass the continue signal, or sig cont, to the job number 1. So we'll say kill sig cont %1. Take a look at jobs, and then we can take a look back at our... Now we're getting game and match, game and match. Remember, we killed job 2, which was set. So we don't see a set, we just see game and match. Notice also that after a little while, that second job fell off of the job's output. Since it's terminated, it no longer shows. It showed for a little while until it was cleanly torn down, but so we looked quick enough to see it, but now we'll no longer see that. Now we want to terminate the remaining 2 jobs and confirm that no jobs remain, the output has stopped, and we use pkill to terminate all tail commands running as our user. And then we'll remove the file. So we'll pass a sig term signal to both jobs 1 and 3. We'll verify that they're both terminated from our jobs output. We'll use a pkill argument against the tail command, and then we'll remove the out file with an rm command. So let's clean this up. Jobs. We can see we're still writing match and game. Now we want to do a kill sig term, and we'll do %1. We do jobs. We can see it's terminated because we were quick enough. Job 3 still writing match. Now we'll do a kill sig term %3. Do a jobs. Oh, job 1 went away. We see it's terminated. Job 3 no longer appending to the out file. And clean that up. If we do jobs, they should be gone, yeah. And now we want to do a pkill. So we want to process kill, sending the signal sig term to the tail that we were doing, yeah. So we go ahead and press enter. And if we go to the other one, you can see that we've returned to the command prompt. It even gave us the helpful output here that just shows that it was terminated. Now, if we just look at the end of our out file, notice that terminated was just on our screen, not actually written to the file. Now we do an ls and we can see the out file, and we're asked to remove the out file. And we do. I'll clean that up and I'll close this terminal, our little monitoring terminal, clean up my screen. And that concludes this exercise. Hopefully you were able to follow along and manipulate those jobs running in the background, those processes, and use both the signals and the pkill command in tandem. That concludes the guided exercise, and I'll see you in the next video. See you there. The concept of load average is a commonly used metric to determine the health and performance of a given Linux environment. This information is provided directly from the Linux kernel and gives us a snapshot-in-time understanding of the performance and availability of system resources over several different intervals of time. As we track the availability of system resources over time, we can understand whether or not performance is degrading or improving, and further go on to track down which processes may be causing this change in behavior. Every 5 seconds, the kernel gathers the concept of a number it calls the load number. This load number is based on a calculation on the number of running processes as well as those that are in uninterruptible states. It accumulates this concept and does calculations to provide us a health report on the load number in the given 1 minute ago, 5 minute ago, and 15 minute ago increments. It's in this fashion, by tracking the trend of that number over these intervals of time of 1, 5, and 15 minutes, that we can determine if a system is improving its performance or degrading in its performance. Remember, the terms are provided in these specific time intervals: 1, 5, and 15 minutes ago. So understanding what the load average calculation is can be a bit complex or puzzling to individuals. You can take for granted that this information is valuable, certainly, but understanding how it's calculated provides a little more insight as to what value it provides. The load average is calculated by the kernel, determining how many processes are ready to run on the CPU versus how many processes are waiting to enter this state. It's essentially a ratio between the processes in the running or runnable state and those that are in a waiting to run state, determining whether or not the system is available to take on more or less work. Depending on your environment, this calculation may vary on what specific information loads into the number. However, the trend over time is an important heuristic for a system administrator to understand degrading or improving health of a system. In general, the determination from a load average allows us to understand how healthy a system is, whether it can take on more processes and provide more work currently, or if it's being taxed to a point of near breaking by the amount of workloads that are currently requested for the CPU and resources. Load averages are displayed in a delayed fashion in those time intervals of 1 minute, 5 minute, and 15 minutes ago. So we're always doing a look back on system performance. If system performance numbers are getting better at the 1 minute time than they were 15 minutes ago, we can assume that the system is recovering or trending in a more healthy direction. However, if 15 minutes ago the load average was in a better situation than it was 1 minute ago, we can understand that the system is in a degrading health. As we look at those three values over time, we can then make assumptions about the behavior of the system and determine what other remediation may be necessary. Let's take a look at a specific output of the command uptime, which is one way to display the current load average. The command uptime displays the current load average and provides us with output that looks something like that in the box. The main point of uptime is to show the information for how long the current boot of the system has been going on. In this case, it shows an uptime of 14 minutes in this sample output. It also shows how many users are currently connected to the system. The information we'd like to focus on here is the load average. Remember that these are shown in the last 1, 5, and 15 minute intervals. Here we can see that the load average 15 minutes ago, a much higher number of 5.2, shows a more heavily taxed system than it was 1 minute ago. The load average 1 minute ago, showing 2.92, shows that we have more system resources available since the number is lower. This means that 15 minutes ago our system was much busier, almost twice as busy as it is currently. We can make an assumption that this trend shows that the system is becoming more available or in a healthier state to take on more work currently than it was 15 minutes ago. By interpreting these numbers over time, we can make those assumptions in a safe fashion about the system environment. When we start looking into what may be causing system bog down or what other processes may be in play, we can start using other commands to gather information about the system and calculate things like available CPU load. We have a helpful command called lscpu, which will determine how many CPUs the system has, as well as critical information about those specific CPUs. You can take a look at the output of the lscpu command here. Namely, what most people want to gather out of this, at least when doing this kind of inspection, is how many CPUs am I working with on this given system? In this sample output, we're looking at a Linux system that has 4 CPUs available. That means that we have 4 different processors that are available for scheduling process jobs. When we start interpreting load averages based on the number of CPUs available to us, we can think of the number of CPUs as a multiplier on this available work that the system can perform. While it's not exactly one-to-one, we can take a consideration that one CPU can provide a load average of one amount of work at a time. In this way, a system with 4 CPUs should be very comfortable running at a load average of 4. Numbers greater than 4 could indicate an issue with system availability and resources, while a number less than 4 means that we have available CPU processing power available to us to do more work. While this isn't a hard and fast rule, it's a great rule of thumb in order to determine a proper load average for a given Linux environment. Other tools that report load average are things like the command W and top. We've taken a look at these briefly, but let's jump in a terminal and just see where load average exists given these commands. If we type the command W, we can see that load average is clearly displayed here. Additionally, if we use the command top, load average is also output at the beginning of its output. I apologize for line wrap, but we can see the output of the load average here as well. That concludes our eyes on our systems. We need to rely on real-time information in order to inspect the processes that may be causing issues within our environment. Real-time processing occurs in the form of a great command called top. Top provides a consistently updating output of the top consuming processes running within your system. It's similar to our PS information, except for the fact that it continually updates, by default, every second. This continual refresh allows us to see trends over time in a real-time output. We get a ton of helpful information to track down what may or may not be causing the issues within our system. So let's take a look at some of the fields of information that top provides us. While we can customize which columns exist, as well as the order of sorting the information to the top output, the default output includes this information. First and foremost, it includes our PID, or process identification number, and the username with which the process is owned. We get a column for the virtual memory the process is using, and we have several labels to describe that further. Resident memory is the physical memory used by the process, as well as any of its shared objects. We then have a column that describes the process state, and we've learned in previous sections about the various process abbreviations, from uninterruptible sleep all the way to zombies. The time field is the amount of CPU total processing time that process has consumed. This can be toggled to also include the cumulative time of all child processes as well. This table shows us some of the helpful keystrokes we use within top output. If you wish to get a listing of the commands in order to manipulate the output top is displaying, you can use the question mark or the H key. When we wish to specifically see things like load, threads, or the memory header lines, we have a key for each of those, L, T, and M. The 1 key will toggle on and off the output of the individual CPUs for systems that have more than one CPU, which is not at all uncommon in today's world. With the S key, we can supply a numerical argument for number of seconds with which to update the output. This can also take decimals, so we can update as quickly as every half second or as slowly as we need to. The B key will reverse the highlighting of the running processes. The default is bold only. Capital B or Shift B enables the use of bold in the display. Capital H or Shift H toggles threads and will show the process summary of the individual threads. U and capital U filter for any username, so allows you to supply that argument. Lowercase u will be the effective username, and capital U will be the real username that owns the process. Oftentimes a user launches a process, but it may run under a different name, and that's really the difference between effective and real usernames. Capital M sorts the output by memory usage, and capital P sorts the output by processor utilization. These helpful keys allow you to read and interpret, as well as manipulate the output of top to help fuel your administrative and investigative troubleshooting tasks. Continuing with just a few other hotkeys for the top command, we see that we have the K argument, which allows us to list a PID of a specific running process and provide a signal to that process. So directly from within top's output, we can highlight and identify a process that we may wish to terminate. We would hit the K key, supply the process identification number, and the signal we wish to send, either the short code like sigterm or the numerical value like 9. While we've not discussed the concept of nice values, there is a preferential treatment to processes going on that the kernel determines. We have the ability to influence kernel decisions on which processes are more important by adjusting a value known as the nice value. The R key allows us to re-nice a process or to adjust its value of importance within the list of processes that the kernel will be self-managing. This allows us a manual intervention to tell the kernel we prefer a certain process be processed sooner or deferred to later in the stack. If we wish to save the current information we're seeing in top, we can write that out to a file using a capital W. When we're ready to exit out of the top output, we use the Q key to quit. Lastly, we can customize which fields are included in top output using the F key. Depending on what you're after with looking at this output, you may care more or less about certain fields, and you can omit the ones that aren't valuable to your inspections. This concludes our section on monitoring processes. Join me in the next video where we go through a guided exercise to test these skills out. Welcome to our guided exercise on monitoring process activity. We're asked to create a script called Process 101 in our bin directory in the home directory of our EC2 user. Let's go ahead and write that out and save it. I'll use Vim to do so. Okay, once you've written out the script as follows, you can go ahead and save your work. Don't think it would matter much, but I'm quite a stickler for the various syntax here, so I'll clean up a little white space, save my file. I can just cat it just to make sure we like what we see, and then I'll chmod plus X. Oh, you know what? Actually, I believe I just wrote this here. So let's move process 101 into my bin directory, and then chmod plus X bin process 101. Okay, great. Now if I do an ls-al on bin, I can see both our forever process from the previous exercises and our process 101. Now this one's going to endlessly perform 50,000 additions. So as we set this in motion, it will reset the variable and repeat after each of those numerical additions. So our process approach here is that we'll start one of these and we can monitor what impact that has on our system. And then we can set multiple of these scripts running and see how that impacts the performance on our system and should end up utilizing more resources as we run more and more versions of this script. Down in step 2, we're going to get into our other window and we're going to run the top command. So let me go ahead and start that going now. Get my new window. Okay, and then I'm going to shrink this one down just a bit. And I should be able to put it here with top. Okay, great. Nice. Got our top output looking healthy. Just keeps updating every, let's see, by default it's every 3 seconds, I believe. Yep, 33. You can take a look right here to see what your default interval is. Mine's every 3 seconds. Okay, so now that top's running, we'll just leave that running. It continues to run. Now we're going to run the command that determines the logical number of CPUs on our machine. So we can grep for model name out of the proc CPU info and then count those. We'll get one CPU entry per CPU. So if we just count the lines from this grep statement, we'll know how many CPUs we have. Model name out of proc CPU info pipe to word count dash count the lines. All right, so I am sitting with 12 CPUs. If you're using your Amazon instance as opposed to my little sandbox here, you certainly have a different number, likely something in the order of 2, or maybe even just a single if you're using that free tier. So in the left window, I'm going to run a single instance of process 101. Easy enough, and we'll cram it in the background with an ampersand. So I'll do a process 101 ampersand. We can see it running back there. And let's go ahead and see if we see it spike up here. We don't yet. Now, in the top display, we're going to use L, T, and M to toggle the load, threads, and memory header lines. We want to ensure that all headers are displaying after we, transform it, but set it back to default. once we have done. So L, you can see we're removing that top line, which has to do with load average. So I can see my load average sitting at 0.81, which is larger than it was 5 minutes ago, 0.77, and probably from our previous exercises 15 minutes ago, I did have some load on the system. But as you can see, currently in the 1 minute ago versus 5 or 15, I can see that my load average is starting to climb. All right, so I can toggle that on and off. I'm going to leave it on. M is the memory information we can see at the bottom here, going through the various ways we can output that info or remove it. And T is going to manipulate that CPU output or remove it, the tasks and CPU section. So I'm going to leave this as default. Additionally, if you have multiple CPUs, you can press the 1 key to show them as individual CPUs or just have it all aggregated. So another way to see that output. So task 6 asks us to note the PID for process 101, view the CPU percentage for the process, which is expected to hover around 15 to 30% on a single CPU. So we want to identify that, and we certainly can from our jobs over here, 231983. And then we can see it here, 231983. It's not going to hold my highlight there, but you can see it sitting there. And we can see the CPU usage in particular. I'm sitting at 13, went to 12.6, but as expected in the 13 to 15% range. In the left window, we're going to start another process 101. Cram it in the background. So let's do another one. Process 101. Stick it in the background. Do jobs so we can see what they are. Okay. And then we can see we have 2 of them here. Here's my new PID. We can see that the load average now is likely to be impacted by that. If we were to look over time, we should see that load average with 2 of these running could be impacted. And we did see that second process start and the fact that it hovered in that same range. So we can see the second instance here. We can see instance 1 and instance 2 fluttering, but sitting in that mean average of 13-ish % of a CPU. Now, step 9 wants us to start another one. So easy enough. So we'll just do a process and put it in the background. Do a jobs on that. 559 being the new process, and it lands right where we want it. Oh, it's kind of nice that this isn't on this screen here. This is from the background jobs output, but I like how that lines up quite nicely. We can see that it is sitting in that same acceptable range. Our load average indeed starting to climb. When we're finished observing the load averages, we're asked to terminate each of these. So let's go back, take one last look around the top output, and then we can start by killing each of these processes directly from within the top output. What we'll do is we'll press K in top in order to issue the kill commands, and then the default signal that K would issue is kill. And so then we just need only either pass in a PID for a process we wish to kill, or if we're lucky, the default PID may match something that we're after anyway. So let's go ahead and take a look at that. Okay, I'm in my top output. If I press K, 134729, no, not what I want, so I don't press enter. I'm looking at the PIDs for the processes that I started. So 232405 is one, so I'll type it 232405. If the default PID here matched one I wanted to kill, I could just simply press enter, but I'm going to be explicit and get rid of that one. So just a verification, I hit enter. And sure enough, we see one of those go. I'll click back over to here, and we'll do jobs. And we can see that I happened to kill off the second one. Come back over, hit the K key. That's not the one I want to kill, so I'm going to type out 231983 and hit enter. Asks me to verify. I definitely verify. Bounce back over to here. Jobs. Terminated job 1. Excellent. And last, kill. Not the PID I want, so I type 232559. I'm getting these PIDs from this first column corresponding to my user's process, right? And so then I fire that one. If alternatively, the PIDs were given to me when I launched each of these jobs, so you could have seen them there as well. You could use PS commands to search and find this PID information, certainly. but it was available right there in top as well as this screen here. And then we could just interact directly through top in order to kill those jobs. So let's see what jobs we have left. The last one's there, and it's gone, and therefore we no longer have them running. We don't see any of ours here, just the stuff having to do with me recording this class for you. So that's excellent. Let's go back to our instructions. Great, now we're just asked to quit the top process. Let's go back here. Excellent, and I'll just hit Q. And that ends my top from running, and I can clear up, no problem. Close off my extra window. Don't need that anymore. And we're all clean. And that concludes this guided exercise. RPM is a particular package management format in which we bundle up all the files that comprise a piece of software. This was originally developed by Red Hat and remains a standard in many Linux distributions to this day. The RPM approach makes it easy to manage all the files that come together to make a software package. The benefit of using this method of an RPM software package is that it easily allows system administrators to track all the files and changes throughout the environment that a particular software installation provided. Along with the software itself, RPM is companioned with a database that tracks each of these changes and files. There's 4 main pieces to an RPM package name. Let's take a look at that. The first bit is the name of the software package itself. We separate each of these fields with a dash, and the second field is the version of that piece of software. The third field is the release of the particular software package, followed by the architecture that it's intended to be installed on. We end each software package with the extension .rpm. This denotes that it's a Red Hat Package Manager specific file. The name for a package is one or more words that describe its particular contents. The next field, the version, tells us the iterated version number from the original software. Next is the release or release number of the package itself based on that version. Each version of a piece of software may have multiple releases. The last field is the architecture. This is the CPU architecture that the package is intended to be installed upon. Sometimes we have packages that have the nomenclature no arch, meaning that it is not architecture specific and could work on any of a number of architectures. It'll be important to make sure that you grab packages that have the proper architecture or a no arch declaration for the system you wish to run them on. Software packages themselves are collected into what are known as repositories. These are available to you from many providers throughout the world as sources from which you can obtain the software packages. When it comes time to install a piece of software, you'll need to know about repositories so that you can retrieve the packages you wish to install. Each RPM package will be made up of 3 main components. The first are the files that are installed by the package. This is obviously necessary for any piece of given software. Next is any information about the package. We'll call this metadata. This is name, version, release, and so on and so forth, details about the particular piece of software. Helpful descriptions of its purpose and intention, as well as any other required packages to make it perform successfully, would also be contained. In the open source world, we learned that there are many different licenses that we can create our software packages under, and it will include the license information for the specific package. Another helpful aspect contained within is the changelog, or the various changes to the software throughout all of its version history. It can also include any other relevant information the software creator deemed worthy of including. This could be further instructions about how to utilize the software or other helpful information about where you can go to for community assistance or even the code base. The next piece is any scripts that'll run when the package is installed, updated, removed, or executed. This is so that the software can properly perform in your environment, but also be managed through its life cycle from installation to removal. While not enforced, software can also be signed with what is known as a GPG key. As a creator, Red Hat itself has a specific digitally signed key that we sign all of our Red Hat packages with. This allows you to verify the contents of the package that have come from a specific owner of the content. If you choose to enforce these signatures, you'll either need to verify that the package comes from one of your signed providers, or the package will not be able to be installed on your system. This is a safety measure to make sure you're getting the software you wish to run in your environment from sources you've decided to trust. Once we install software, the next piece of its life cycle is to update software. RPM packages are created in order to provide this particular path forward with software you've already installed previously. When we do this, RPM allows an easy way to track the process. In general, the steps are to remove the older version of the software, install the new version of the software, and keep track of all the changes that have occurred throughout this process. Since we're moving from installed software versions to just their newer version, we'd also want to make sure that any data we've created with that piece of software is preserved between versions. The scripting to provide this particular process is usually contained within the updated environment's packages. In our previous section, we talked about RPMs. RPMs also express a command, the RPM command, which lets us inspect and manage the software installed on our system. Now we'd like to look at another way to manage this same sort of work. Namely, we'd like to learn about yum, the yellow dog updater modified, and its corresponding yum command. RPM provided us a low-level way to install and inspect packages. Now, with yum, we have the ability to hook into repositories, search for global software, and use a different interface in order to manage the installed software in our systems. Yum is intended to work with RPM-based packages, but is really an interface that allows us to find and manage the software we are installing inside of our environments. When it comes time to use yum, we'll start with the concepts of using yum help, as well as how to list out the various files and software that's available to us to be installed. The yum list arguments can help us search for and find software in a very easy fashion throughout repositories located globally around the world that are available to us to install in our Red Hat environments. Here you can see the yum list argument searching for a package named HTTP. The HTTP package helps us find the available web servers as well as other HTTP-based tools that are available for installation in our environment. The list command displays all listed and available packages that correspond to this search term. We also have the concept of yum search. Yum search takes in a keyword and lists packages by that keyword found within the name and description summary of the package. If we were to search for the term web server, we would find in the output any package that contains the phrase web server in its description or name. That would include any number of things that may or may not be intentionally what we're looking for. If, for example, we were looking for the Apache web server, we could find Apache HTTP server in many ways. It would be caught with this particular description, but the description for web server also matched the Apache HTTP server. If we wanted to know more about the various packages we're finding available to us through yum, we have the yum info command, which takes in an argument of a specific package name. This will need to match the exact name of the package and not just some term found within its description. If we wanted to look deeper at the Apache web server package, we'd need to know that its package name is HTTPD. If we did, we could type yum info HTTPD and see all the relevant information that is available to us about the specific package we have available to us within this particular Linux environment. Another keyword we have from yum is yum provides. Yum provides is followed by an argument for a path name. If you wanted to determine which package made available to you a specific path name, you can use the yum provides argument. An example here shows us with using yum provides and the path var_dub_dub_html that we're actually inheriting this particular file and was created by the installation of the HTTPD file system package. This is a component of the HTTPD installation that created a directory for use for web-based content. If we were unfamiliar with that behavior, yum provides would explain to us where this directory was created from. When we're ready to actually install or remove software, yum has keywords for that as well. We've determined that the HTTPD package provides us the Apache web server. If we were to want to install that, we'd use the yum install command followed by the package name HTTPD. What's nice about yum is it'll do a lot of the homework for us in order to resolve anything like dependencies or additional software that needs to be installed on the system before we can install the Apache web server. If this were a simple RPM interaction, we'd have to manually add those particular dependencies one at a time. With Yum, we can allow the Yum system to install all dependencies that are required before installing the software we requested. This can be done in a single command. If we already had the HTTPD package installed, we could use a Yum update statement to update to a later version. The Yum update statement takes an argument of the matching package name and then installs any newer version that may be available. It'll perform a check to determine if this is available, check for any dependencies required before installing the update, install the dependencies, and then install the updated version of the software. This can alleviate a large number of headaches a system administrator may go through in doing this work through an RPM-based interaction. By automating that, you save a lot of time and efficiencies that are quite valuable to system administrators. The last major command that we have for Yum to manage the installed software in our system is the one we use when removing software. When we're ready to uninstall software, we can use an argument for Yum remove. This again takes the package name argument and removes the installed software package. Here you can see an example of a Sudo Yum statement because software management oftentimes is required to be run through administrative credentials. Moving forward, Yum also has the concepts of software groups. These are collections of software that are related to one another to provide a specific function or feature. This can comprise pieces of software that are mandatorily installed together, a default set of choices that are usually installed together, and even optional pieces of software that may be added on. These optional pieces of software are not required, but may enhance or add a feature that you're looking for and can be installed in this group fashion and managed through Yum. Like the Yum list command, we also have Yum group list. This provides a similar feature except works on software groups. We have many other companion Yum commands that work on the group collections of software, such as Yum group info to display information about a group of packages, or Yum group install if we try to proceed with the installation of those particular pieces of software. You can see that when we do a Yum group install, we typically include the name of the group in quotation marks, as they're usually longer than one word and are more of a descriptive set of words to describe the pieces of software that collect together to provide a function. In this case, you can see the example of the RPM development tools. This is a collection of pieces of software that cooperatively work together to allow individuals to author their own RPM files and manage them through a workflow. Rather than installing each of these pieces individually, the RPM Development Tools software group is able to be installed with Yum using a group install. Once you've used Yum in your environment long enough, you may need to peruse the historical information that Yum makes available to you. Transaction logs are kept in the location var log dnf.rpm log. This allows us to see the various running tab of software that's been installed, updated, or removed from the system. The command Yum history will display a summary of the installations and removals of software by reading out this file. If we ever need to undo a specific transaction, we can rely on the history to do that as well. Yum history undo, such as the example shown here, will undo the fifth piece of entered information from the history. If we look to the output above, we would see that was the installation of HTTPD on ID line number 5. If we say Yum history undo number 5, it should reverse those steps. Included here is a helpful list of commands that we'll often use with Yum. Be sure to be familiar with these as you work with software installation and management using the Yum utility. That completes this section. I hope to see you in our next section where we do a guided exercise with these skills. See you. Welcome back to our guided exercise on installing and updating software with Yum. Here we'll use the Yum package management system in order to install and update software with our system. Alright, so let's attempt to run the GNU plot command. So we'll just start by running it, no changes made to the environment. So we say GNU plot. I can already tell it's not tab completing for me, so alright, so it even makes some suggestions in my environment that, hey, you might want some of these before it's going to work out. So now let's go ahead and do a switch to the root user and search for the package using a yum search plot command. So sudo su yum search plot. And we should get some results there. Great, and we do indeed get a plethora of output there. Now, depending on your environment, you may get more or less, more or fewer output from the search here. Let me just search back up and make sure I can find that we're all going to see that same GNU plot. I can tell I've got it out there in the wild, so if I just scroll up to the G's, we should have no problem seeing that. I do, in fact, have all the GNU plot bits here. I just happen to have a lot more in this environment. But such is life. So, got our yum search GNU plot. We definitely see that we have it in the wild. Now, we want to use another yum info command to find out more about this package. So, I'll say a yum info GNU plot. I'll clean my screen. And I get the information, the release information size, the source name of the file here. You can see I'm using a Fedora repository. It should be quite synonymous to what you're seeing in Red Hat or CentOS or other Red Hat family OSs. If you're using other systems that take advantage of Yum, you'd likely have something quite similar. And we can get a short description of what it is for the command line driven interactive function of plotting program. So we have determined this is necessary in our world. So let's do an installation using the yum install command. I'll clear my screen. Nope. And we'll yum install GNU plot, which reaches out, finds it out in the world, and says there's a few dependencies that are going to need to be installed along with it. If you're okay with that, you hit Y and you press enter, and away we go. The installation is quite automated from there. It installed several additional packages and is now complete. So it resolved those dependencies for us, found the packages that met those dependencies, installed those in tandem with our GNU plot request. So we see that we had 3 installed in my environment, and you may have a slight variation there in your environment. So just depending on how many were necessary to get your system from its current state to the state where GNU plot was a functional tool will be the answer for you. Next, we want to test out this new command. So let's go ahead and just run GNU plot now that we should have it found. I went ahead and tested that out with a tab command. I typed GNU tab and it went ahead and found this. So I'll go ahead and press enter. We're now in the GNU plot prompt. If we wanted to quit, we could, or we could now interact with this. So as the instructions state, let's go ahead and quit out. And let's test out the yum remove command. So we're going to do a yum remove on GNU plot. We're going to say no and not actually remove this. But a fair question that we can answer at the end of this is, how many packages would be removed? So let's do a yum remove GNU plot. Remember, we're not actually going to say yes to this. All right, for me, it would remove 3 packages. I'm going to say no and back out. Operation aborted. So we did not do that uninstall. Now, in this case, much more available upstream and necessary from a base Amazon EC2 image. It would require 59 packages if, for those of you using our Amazon EC2 instruction set to get a free tier EC2 instance. So we said no, we didn't do it. So now we want to do a yum remove command to remove the GNU plot common package. Again, we're going to respond with no, but we want to see the delta of how many packages would be removed from our system. So yum remove GNU plot common. Now I'm going to clear my screen before I press enter, not to confuse you. Pressing enter. For me, again, the same number of packages. 3 are going to go away. If you're in that base image, you'd probably be seeing that 59. I say no and I abort that procedure just the same. Now we want to inspect some things with yum group list. Okay, so we want to gather information about the RPM development tools group specifically, but let's do a yum group list to see all the groups available to us. All right, let's see, yum group list. All right, and we do have quite a bit available to us. RPM development tools is what we're looking for. So close to the bottom there on my output. Yours may be located in a slightly different place. Just remember there's small variances between, or maybe not small, but here, some small variances between Fedora, CentOS, Red Hat, Enterprise Linux. So depending on which one you're using, results may slightly vary, but we should see that output. So we were able to find the RPM development tool. So now we'll do yum group info on RPM development Tools. And there we get the various mandatory packages, default packages, and optional packages that'll be installed if we were to interact with an installation for this group. So now let's go ahead and try it out. Let's do a yum group install on that RPM development tools. Now, if you already typed it once, just up arrow and you can go back and do a yum group. Oh, I shouldn't have even gotten rid of that in. See, could always be more efficient. We do a yum group install. It should go and peruse all of the necessary bits to install this. Resolve all the dependencies. We go from a few packages to a few more with the dependencies. Now we're going to go ahead and say yes so we can proceed with this. And we can see it downloads these packages. Should then go through the step of running some transaction checks. Yep, real quick. And then it did some installations and verifications. And then it lets us know the specific list of packages that were installed. If you were on the Red Hat base image, you'd be missing a lot of these packages, so you'd end up with a big old chunk, 74 packages, as the sample output shows from a Red Hat environment. Now let's explore the history of options of Yum. Yum history allows us to sort of look at the transactional record of interactions we've had with Yum and either play back or forward or even just peruse those various interactions we've had. So let's start by just simply clearing the screen and doing a Yum history. We can see I've had a number. I have 9, it looks like. Even more if I keep going up. Here we can see those latest interactions I've had. So that looks good. Now, if we want to use the yum history info command, we can supply information about that specific line item from the history. In this sample output, because not much has been done in the yum interactions here, the line 6 corresponds to the one where we did the group install. I'll take a look at my yum history again. And I'll see that when I read it, my group install interaction was this one here. So now I want to do yum history info on number 18. But either way, the one corresponding to your RPM group installation, RPM development tools. Oh, got to type it in the right order. So yum history, then info. And now I want number 18. Clean that up a little bit. All right, we can see the packages altered, the various timestamps for when that occurred, and so on and so forth. Looking good. We can now take advantage of the yum history undo and undo an uninstallation. Particularly, we asked to look for where we installed the GNU plot package. So in our sample, it is line item number 5. Let me take a look and see what it is in my environment. Your environment may be different as well, especially if you played around with some of this stuff throughout the chapter. So if I do a yum history, looking for that GNU plot, here's line item 17 for me. So what we end up wanting to do is a yum history undo that line item. So for me, it's yum history undo line item 17. I'm going to clear my screen, and then we'll press enter and see what happens. Okay, now it's exactly what I was looking for, the removal of the GNU plot. Let's make sure we're intended to proceed here. We are asked to actually perform this uninstall, so I'll say yes. And it goes ahead and it strips away all the packages that it told me it would. Those 3 packages in my case, likely more in yours. All right, last we just want to perform a system update using a yum update command. Again, we'll have an interaction where it asks us whether or not we wish to proceed. So we'll certainly say yes to that. Updates are always good. So let's do a yum update and see how many we need in this system. Again, results may vary. Here I don't have a ton. It's 7 installations, 7 packages, and 319 upgrades. So I'm going to go ahead and say yes to that. And away she goes. So lots of downloading. It'll grab all of these packages, do that quick transaction check, install and verify all of the above. Can take a bit of time. So food for thought on when you might want to perform this work in your daily grind on your own systems. Because this is something that could take a bit of time to perform. And additionally, when you're talking about things like certain upgrades like the kernel update I see listed there, some of those could actually require a reboot before you're picking up those changes. So scheduling that into your workloads and workflows may not mean that you're doing it immediately. However, for learning purposes, it's obviously A-okay that we're going ahead and doing an update. I'm going to go ahead and watch this one so we can see all the kinds of things that flow into my environment here. All right, hopefully your upgrade went just as well, and we likely have considerable differences in the types and style of packages we installed, just depending on our environment. Either way, we can see that it was as easy as pie to go ahead and update our system using Yum. That concludes this guided exercise, so I look forward to seeing you in the next video. Welcome back to the conclusion of our course on Fundamentals of Red Hat Enterprise Linux. We've come a long way together through this series of videos to help explore the world of Linux itself. We've learned about Linux and the open source environments that Linux creates, the community that exists to help us all develop the greatest tools, software, and operating systems, as well as to provide support to one another as we utilize these pieces of software. We have a number of topics that we went through that help us understand how to begin our work within a Linux-based world. We immediately got onto the command line and started learning commands that help us navigate and manipulate an operating system like Linux. We opened and organized and edited and saved all the files that make up the elegant hierarchy of files and directories that comprise a Linux operating system. We created and managed our users and groups and understood the security implications about group ownership and the permissions set on each. From there, we took a look at all the processes that run to make the environment work to meet our needs, as well as how we inspect and manage those processes in real time. Lastly, we started looking at how we manage the software that runs in our Linux environments. From an installation through its lifecycle to removal, we're equipped with the tools to manage that environment and the software running within. If you'd like to revisit any of these topics, please feel free to peruse backwards in our course and revisit those specific videos. I encourage you to try all the guided exercises and labs several times until you feel a mastery of these skills. I hope you enjoyed learning about Red Hat Enterprise Linux and all of the tasks that a typical system administrator has in their tool belt. On behalf of Red Hat, thanks for joining our course. My name's Chris Cayuette, one of the senior content developers at Red Hat. Thanks for attending, and I hope to see you in our other courses.